that projecting? Was like this that you prefer, or yes. This? Okay. Now the point is, if I get okay, 9 a.m. Can you hear me? Right. Okay, perfect. Thank you. And so let's start on the point where we stopped yesterday, pretty much. You go here, remember, open on demand. Here you land on this page. Click here. I will be creating a new session with Jupyter. Again, I will not be using the GPUs. Could use it, but how many people we have? We have 34 here, 5 here, 6, 5. Eventually, we can try to use the GPU. So if you want, you can try. In that case, it's slightly different. You select here Python via Singularity and standby 4 hours. Let's say the first share is, in that case, if you are using the GPU, is to request 8 CPUs and 1 GPU. And for the
you share your screen.
Oh, I'm not sharing my screen. Great. Yes. Okay. So let's see. I will try. We have around 45, 50 people. So half of the people who register, which give us the chance that eventually most of you will get a GPU if you request it. In that case, that's what I will be doing here, selecting Python via Singularity, which allow me to, well, in a minute I will say, standby here, I will request 4 hours, 8 cores, 1 GPU, and Jupyter. And for the first part here, I will be selecting TensorFlow. This is the framework that I will be using for this first part. We'll continue with the digits. And hit launch. The reason why I'm requesting, so typically we have on GPU machines, we have 24 cores. and 3 GPUs machine on three GPU cards on that machine. So the first share is 8 CPUs per card, per GPU that you are requesting. And it's what happened. I forgot. Yeah, I forgot to do something. Yes, I have to correct this. So Python via singularity here, instead you select COM GPU inter. So this is the queue. The standby queue doesn't offer GPUs, only this one, COM GPU inter. So let's see, GPU via Python via singularity, COM GPU inter, wall time 4 hours, 8 CPU cores, 1 GPU card, and Jupyter NGC. NGC those are the NVIDIA optimized containers for a variety of framework, deep learning frameworks, and molecular dynamics codes, and things that can have advantage of GPUs. So you hit launch, and it should be, let me open the chat, just okay, so you can see that. Okay. Okay, so some people, yeah, send you the link. Thank you. So you will land in something like this. So you see one node here. You will see one node, a core is running for 4 hours, and you hit connect to Jupyter. You go to Scratch, deep learning, notebooks, TensorFlow, this one, 1B TensorFlow. What I'm putting here is because I am offering you a little bit of experience on different frameworks. So you see in parentheses, which is the framework used on that notebook. So you need to pay attention to that if you want to execute on something very particular that only offers one of the frameworks. The C Python, I installed all the frameworks, not optimized, but I installed all of them to have something more generic. So let's start with this one. I will be healing this, clearing the output. 1 GPU, 1. We will be using just one here, 1 GPU. So let's start. We already comment a little bit this at the very beginning, so you will be using TensorFlow. Now this time, I'm not reducing for me at least, the number of cycles that will allow me to show you a little bit better the issue with overfitting. So I will show you that we are collecting the data from a file. They have 60,000 training, 10,000 testing sets. We already saw this yesterday, the images, and the kind of things that we are doing here next is transforming those 28 images into a long vector of 784, converting that into a floating point number and divided by 255. So you get a number from a real number, a truncated real number from 0 to 1. That is for facilitating the work to the neural net. This is the simplest way in Keras. Let's see what it's saying. Yes, you see here the red message about what it found. And there are other ways to see this, that I'm using a Quadro RTX 6000. This is the card that I got. We have RTX 6000, and the first generation of the first time that we bought this cluster, we called P6000, which is the previous generation to that. They also have 24 gigabytes of GPU RAM, so they are sufficiently good for this. And we have a few business in economics that have one A100, they have 40 gigabytes of RAM. And so you see here how you build. This is the easiest way of building a neural network, especially for dense net. There are layers, so in sequence. So you offer a list. If you know, we saw you this yesterday. For those, you were offering here a list. It's a list of objects of the class dense here.
Which Python version did you use?
Which what?
Python version.
In this case, let me see. This is a Python 3.10.0. But again, maybe your question was, what was my selection?
When launching the job. Yeah. The notebook.
Which one?
The person was asking when launching the notebook, what version?
Oh, when I load the module, let me show you here. What I select was here, Python via Singularity. It's the last option in the list. Python via Singularity. Instead of this one, you can use this one. If you get in trouble, because now we are growing a little bit, the number of people, we have 48 here plus 8 here, we're probably still fine. If it doesn't work, you can just change to the C Python 3.10 and change this to a standby and don't request a GPU. It will be fine. It will be just slower, but the math will be exactly the same. There is nothing fundamental on that. It's just speed. And for you to get an experience on that, you will see that it's significantly faster. So this is the digit. I already checked this. I already built the network. You see here, this network is 64. So the input doesn't count here. 64 first hidden layer, 64 second hidden layer, and a final dense layer with 10. Those are the 3 layers, 55,000 parameters to fit. A brief explanation of what I showed you yesterday, why the softmax exists, what is the reasoning behind creating that equation. It's not magic, it's not a God-given rule or something. There are reasons why we put this equation in this form, and I would like to transfer that. So what I did here was selecting some random numbers. So imagine that the value was this. What happens when you take the explanation of that? So you see that even if I have negative numbers, all those became positive numbers. They squeeze them. And after, what I'm doing is dividing by the sum of that NumPy array. So I am getting a set of values, and those values are here. And you see that we get a very predominant number. And all those, at least a linear scale, they look flat. Only when you plot this in semi-log, you see that there is some features here. So that is the justification for the next part, which is why we are selecting those things, the categorical cross entropy for the last function, why I told you yesterday, why this is well balanced, so the accuracy is a good metric for us. We don't have to go into a confusion matrix or something like that we'll eventually explain later. The idea of the categorical versus an explicit array. So that will be skipping all this. And now I am fitting. This is where the GPU is actually doing something. You see that the GPU do those things really, really fast. They are processing every single time it's moving. A lot of things happening there. It's changing little by little all those 55,000 wakes and biases, and wakes and biases. All those are optimizable parameters. And is, of course, for doing that, is also storing a lot of partial derivatives of all the dependencies of that in a cascade. We will see that in a minute in the future notebook about the math behind those things. So now we see here the accuracy that we are getting. But the main message here is that I asked for 40, in this case with the GPUs, I asked for 40 epochs. So 40 times the entire data set, the entire 60,000 are moving through the network, checking the output. The output will indicate how to change the weights up, down. Some of them will indicate that should go up, should go down. It will be an average. That will change in a cascade the whole weights. And after again, all the 60,000 images moving again into the network will do the same thing over and over. And you see, with every pass, we are also taking this here. We say, okay, do a validation with the test data. So we, in this case, we are taking the data that was not used during the training to check how good or bad the model is capable of capturing the patterns of the digits. So you see that at some point here, the training there, the test data is not getting significantly better. It's just flat here. So what I told you is that after epoch number 6, what the network is doing is just remembering. The patterns that are remembered are not generalizable. They are just capturing a memory on those digits that are presented over and over the way. So the weights are tuned for that, not capable of generalized or be general enough to capture those that are unseen data. And you see this with another way, with the history. So those are different equations, two different ways of looking at the same issue. And the losses became kind of flat or slow, small slope. But here is going down, 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 down. So what solution we can offer? So the first thing we can do is, okay, let's do this bigger or thicker. So what I offer here, my proposition was, okay, what about if all those 764 go inserted in a first layer with double the size, 128, and after a second hidden layer of 128, and after the 10 outputs that I will use for. So it's, you see here, that increases the number of parameters here significantly. So now we have receiving 700 times 128. So that goes plus the biases. So that gives us this number. And after we have all those 128 connected to all those 128, so that will give us plus the biases, will give us this number and this number. So a total of 118 parameters. So we'll say, okay, great. Now we have more parameters that should work better. Again, same idea here. So we are using the same laws, the same optimizer, everything the same, except that now that our neural network is just bigger. So again, I'm running this really fast. Okay, so I think it's done. You plot, you get pretty much the same thing. At some point, even sooner, at the end here, we will see it's slightly better. We will make a comparison at the end. But still, there is a point where the patterns are not captured anymore. It's just remembering, and that the technical term for that is we are seeing some overfitting here, and the same happens in semi-log with the losses. So what? Now we have one, the original, the bigger. Now we'll see is deeper and better. So what I'm doing here, instead of, I got back and say, okay, let's see 64. But this time I would like to make it 64, 64, 64, 64. So I'm making more transformations. I'm making more changes to the way, trying to see, okay, maybe this is something that could help us. Making the neural network deeper. So now we have 64 here, but we have more layers. So we are increasing a little bit the number of parameters. They don't increase as much as making it bigger. We have 63. Remember that the first time we have 55. And so I will launch in this. It will take a minute. I will in any case ask for this one and this one when they are ready to plot. So notice that all those 64 layers, what they are doing, are transforming the data. It's like changing the way you see the world for all those pixels in another representation, in another dimensionality. So now we are having 64 dimensions, putting those, transforming those in another world with 64 dimensions, another world, 10, and trying to fit all that. So is this one deeper? Yes. So you see, same happening here. You see, it's hard to say if you compare just image with image. You will see at the end what we'll see is better with the training. It's not particularly better with the test. We see almost the same part. So what I quick detour here for a nice phrase that the grandfather of computing said once, that with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. So someone I found over internet one paper in the American Journal of Physics, where someone actually did it with complex numbers. So now think about why this is a function. Why this is a function. So you see, if I saw yesterday or well, for the afternoon, a function should have only one return to the group. It's simple, but anyway, we'll skip. It's a complex function, so the domain is the plane. It's not the x-axis. So now, what is happening here? We have here is a summary, 64, 64, 10. Well, that's what we are getting. This is the validation accuracy. So we are getting better, but not particularly bad. Still, this is a very simple example for today's standards. So the idea is in physics, or one of the big lessons in physics during the 20th century is follow the symmetries. The symmetries are a powerful guide for many things, also in chemistry, in many areas. And we are losing something when we are converting that image into a long vector. We are actually losing a couple of things. And one thing is the fact that if you, as a human, I hope you can see I present you with a number here, 9. I hope it's visible. Yeah. And I offer you the same 9, but a few pixels move. I just move a few pixels. From the point of view, this way of doing things, making this in a long vector, is a completely different. It's a completely different arrangement of pixels. So for us, it's the same number. You can take the figure and you move it 1 pixel. It's the same number. You don't have any problem checking that. So we are using something that is central in physics and images, is the translation invariance. our way of converting this in a long vector is completely destroying the translation invariance of all this. What if we can do something that tries to capture that so it's better? And that's the solution with convolutional neural networks. It's really simple. It's really easy to understand. And the big highlight, or something that became make this topic hot, was this paper in 2012, where these researchers using a convolutional neural network that is like this. I will explain you in a minute. It's rather complicated visually, but you will see that it's something really simple to understand. It was capable of a significant, like almost 10% better for a large image. Yes.
So can we know beforehand, like if we add the layer on neuron, the model will increase or not, or we have to try with the code?
What do you mean?
I mean, before adding the layers, do we predict like whether our model will improve or not, or somehow?
I still don't understand.
Yeah. So I'm saying, like, as you are showing us, so you are adding layers, or sometimes adding more neurons to see that whether the model is improving or not.
Yes.
So I'm saying, can we predict beforehand, like if we add more neuron, our model will be improved or not?
Predict before?
Yeah, beforehand, like.
Well, you have intuition. We have there is a balance. Everything in life is a balance. From one side, we are adding more parameters. Yeah, but more parameters, okay, is better because you can fit a function that is very complex better. But it's also a danger. If you see here, if someone give you experimental data of someone throwing a ball or something, and they will send you some points here. And you make the equation something like this, a parabola. Yeah? And the parabola say, okay, it's fitting the numbers, with some of them are a little bit off here. Well, I can give you, for sure, a polynomial order 5, which will fit this very well. Let's say probably we'll do something like this, or something like this. We'll capture all that, but it will destroy the figure entirely. We'll create a lot of things. So putting a higher order polynomial will not fit better. And you don't should assume that just because it's passing for every single point in the curve, you are getting a better fit. So it's a similar idea. When you are adding more parameters, you have more flexibility for the network, but you are also more you are riskier in the chances that you end up overfitting. And that's exactly what is happening here. So we open this, we make a huge network. Well, not so huge, but let's say the deeper was big. What you saw here, 100,000 parameters. And it was actually showing exactly the same issue. Really quickly, it stopped learning and start remembering. So there is no way, let's say, from outside, I imagine theoretically, and the theoretics behind this is complicated. To say, okay, this should be the ideal size of the network. We just have intuitions that at some point, bigger is not better, deeper is not better. But maybe you should change the way you think about those. Yeah. Question. I can see each epoch is going through only 64 data. So what you say 64?
I think that's the number of mini batches. But when you're training, it goes like 1 over 469. I think that's the number of mini batches. Right?
Yes, probably. Yeah. Yes. So we will see that all those details. So I am peeling this as an onion, so I am passing on or some things. And again, I am trying to make this like recursive. So we will come back again to these ideas. So this is the paper, and this is the idea of convolution. Imagine that you have the image. The image, you offer some pixels here, and I put some names on those pixels. And what we have is another matrix, tiny matrix, typically is 3 times 3, 5 times 5, something like that. It could be bigger. For those cases, small images that we are dealing with is typically 3 times 3 or something like that. And that we call a kernel. And here is the output that we will be getting. And I will show you how we take that. So take this image here and overimpose it here on top of your image. So we are keeping the image as it is. So we are not stretching that. We are taking the image. And now we are taking this kernel with W, X, Y, Z and overimposing on this corner of the image. So now we are multiplying all those. I'm getting some. So that's what I'm doing. And I will show you that how that mathematically translates on what people in physics, mathematics, engineering understand as a convolution. But this is a convolution with images. So the idea is similar, it resonates, but there are some nuances here. We are not inverting. There are some mathematical things that are not happening. So now we have this image, and this will help us to compute this. So again, this is the equation. We are taking A times W plus B times X, E times Y, F times XZ. Summing that, this is the value that we store here. And now we will be translating the kernel. Could be just one space. It could be just 2 spaces. You can decide that. Typically, for those cases, you just move 1 pixel. So we will be covering X, we will be covering B, C, F, G with the kernel, making all the operations, getting the next location key. Here we are doing that, and we are keeping the rule that the kernel only can overimpose, so be over an entire section of the image. So we are not translating to places where the kernel lies out of the image. We end up with, in this case, with a final map. This is like an image map that is 1 pixel shorter on the X direction, 1 pixel shorter in the Y direction. So it's a little bit smaller image. So for example, for the last point, you see here big, we have GW, all that operation. This is the equation that we are computing there, and we are getting this at the end. And this is a convolution. So now you see what convolutional neural is. It's not, it's just more a fancy name, but let's see what, we are doing something more that I will explain now, but I will reiterate this later, is that we take the image, we compute the convolution, and actually we are computing many of those convolutions with different kernels. Again, those kernels are ways of capturing patterns in the figure. You don't decide how those patterns should look. It's the neural network who will learn which are the right patterns to capture the features on it. So those are trainable parameters. Those are W's that you will train. Weights, there are no biases here in this case. And after, typically you do something more. That is, when you have this image, you can take, this is really small for showing that. You are taking like 4 of those pixels, and you are getting the maximum value, and you just keep that. You take like 4 pixels here, those 4 pixels here, you just look at those, check which is the maximum value that was there, pick that one, store that. This is this is called a max pooling. And here we are showing a max pooling 2 times 2. Usually that is the block that we use. So a convolution plus a pooling, this is one thing. Eventually you can stack collections of the same theme. So a convolution here followed with a max pooling, a convolution followed by max pooling. At the end, what we are doing is that we have another thing that you see here in this figure is really nice. You see that we are getting a number of those kernels, so a number of the maps produced by those kernels. As we are moving deeper into the network, we are making them smaller maps, but more maps. So we are decreasing the size, but making more of those conversions. At the very end, we get some many tiny little maps. We flatten all those. We build a dense layer here that we inject into the final output that will be what we will be training. So that is how typically convolutional neural networks work. This is another example with an image with some numbers. So you see, imagine that for some chance, the filter, the kernel, end up being these numbers here. So it's 1, 0, 1. You see, you can take here this corner of the image, compute the additions, sum, and you will get this number 2 here. Notice that this map here, the output map, is a little bit shorter compared with this one. It's just because we are using 3 times 3, so we are losing 1 pixel on one corner, 1 pixel on another corner. So we are getting with a smaller image at the end. This is in math.
I have a question.
Yes.
In the diagram you had up there, and just a little bit of
this
24, N1. What does N1 or N2 mean?
The number of channels. The number of kernels. So the number of different things like this,
okay,
that you will be using, that you will be the weights. So you will get a stack like cards. You will get a pile of those. The different kernels will produce. Let's say, imagine that you have 24 kernels. 24 kernels. When you project those, make the convolution with this image, will produce 24 results, 24 images, maps like this.
Okay.
So that is your pile, your stack. That is what you see here, like this stack of cards are the outputs that you get. Those will be the inputs for the next kernels, which will produce another pile. Well, this is after the pooling. So you get an image is half of the size, 1/4 of the number of elements, because you are making 2 pixels, just one. So the max pooling here, you get this N1 channels with shortened image. Now you have another number of kernels, so N2 kernels, that will produce a bigger pile of a smaller cards, smaller maps, that now are 8 times 8. So not in the pattern here. We have 24, 24. After the max pooling, the size is reduced to 12 times 12, because every 4 pixels is like doing a zoom. 4 pixels became just 1. Now, after that, we are injecting that with another convolution. The convolution you will be losing 1 pixel here, 1 pixel here, 1 pixel here. It will become smaller. We are actually losing more than that, 4 pixels. Yes, 2 pixels. Because the kernel is 5 times 5. So you are losing 2 pixels on one side, 2 pixels on another corner, 2 pixels on the top, 2 pixels on the bottom. That's why you move from 12 to 8 in this image, in this example. So you will get bigger pile of maps that are tiny images. Those at some point after the pooling, they are tiny images, 4 times 4, many of them. And 2 could be hundreds. And after you take all those numbers and you stretch them, you flatten the array and make a big array of flat that you inject density to the final outputs. And that's how you build a neural net. So after you know the different building blocks, the magic dissolves and you see what is happening. And we will be understanding all that. There is not magic here. There are reasons for why people choose those things one by one. And so again, this is what the it was clear the idea of the yeah, okay. Why bigger pile for N2 compared with N1? Okay, that is a good thing. I can answer it right now. The idea is that you are converting. Each map is a filter. It's trying to capture features on that. The typical example is that if you are trying to recognize eyes, so an eye. Imagine that this is an eye. So what the first neural network is doing is trying to capture like edges, things like this, okay, something like this, something like this, an edge here, something that is curvy in places, curvy here, curvy here, curvy here. And so it's building little pieces of the image. After deeper and deeper convolutions are capturing, thanks to the max pooling that is making the image smaller, so getting the image from far away, be able to capture more complex features, like connecting this with this, and making something that is like this, plus something that is like this, something that is like this, and every pile becomes smaller than looking for, but it's capturing one a more general landscape of the thing. So more far away, a more global picture of the thing, which is what the image at the end will tell to the dense layer. Okay, there is an eye in that picture. There are another eye in this picture. There is an ear in here. There is, okay, this is a human being, or this is a cat, or this is a dog. It's capturing more abstract mappings or transformations of the data. So we are making the image look from far away, thanks to the zooming. We are moving to a bigger pile of features on more complex landscape. So that's why we are making the images smaller, but with more features. We're changing that point of view of things. And that is one of the tricks that was a success. It is explained in the paper from Alex, from this paper. If you see here, the ideas behind those, the selections of making smaller or smaller. The idea why the kernels for this kind of problems, 28, you see here, for example, you have a file. You have a file. So the network will probably, and it's 28. So with one, if you see the original figure in one small corner, you have something like this. Is 1 pixel here, 1 pixel here, 1 pixel here. So that is capturing the edge of the file. Here is a curve. So those tiny 3x3 are able to capture small curvatures, more features here and there. And after the pooling is like zooming, and after you are trying to see if there is an edge connected to a curve. So maybe this edge with a curve it's just the way we understand the way the neurons are working. Capturing features from far away, more complex, more in number. The channels, okay, the channels. We have here the image. We have here what we call the kernel. The kernel is a matrix. Those are the weights that we saw for the dense layer. We have and the number of weights is related to the number of inputs that this neuron is receiving. In this case, the kernel has 4 weights, no biases, just those 4 numbers. And notice that those 4 numbers will be acting on one portion of the image, one small section of the image is doing the computation that we saw here, this equation here, and that is the result. But we have several of those. We decide how many we want of those. So that the question is, the channels are the number of kernels that you will be using to try to capture the features on the image. It's possible that virtual by canals, quick question. Yes, sure. Unmute. Can you unmute? I don't know if you can. I can.
Probably can. I don't know if you'll be able to hear, but
yeah, I don't know if because I have the speaker, but I'm not sure if I can hear you.
Hi, can you hear me?
I think unmute from the participants.
Wait, let me see if I can do it.
Oh, can you hear me?
Yeah, see, someone is talking.
Yeah, but I'm sorry, I'm not able to hear, except if, no, I'm not able to hear you.
You could try on your laptop.
Yes, that's one, but I don't want this to capture feedback.
Well, you can mute yourself on the laptop, but with the audio.
No, it will start and give me a feedback. I was expecting that. So I turn off the. Can you elaborate the question if you can?
Can you hear me now or?
Try to write the question.
Okay, I can write it.
So I will be trying to answer the questions why bigger pile for n compared to in1. So the answer is we are making the figure, the maps, that's the name of it. So this is no longer a figure by itself because it's no longer something that you will see and recognize. It's just a map. So the output of a function, the function will be a matrix operation, a matrix sum, plus partial sums plus sums, like a dot product if you want. So this is the output. And how many outputs do you want? So it will be the same number of kernels. So the image will be smaller. After the max pooling will be even smaller. So it will be something like zooming, like looking from far away, you will see other things. So now we would like to capture more features. The complexity will go as you move far away. From very, very near, all what you see are edges, curves. So imagine what you can do with 3 times 3 pixels. It's not much. It's seeing, for example, that this pixel is this pixel, this pixel are there. This is one edge, if you want, and something that imagine that another thing could be, okay, there are X's there. So something that is like crossings in the figure. So that will answer with a big number for that section of the image. When you get the map, this will have in this corner a big number, a high number here. When you move to the next image, probably will get and also still trying to, the X will be there, just translated. So it will capture probably smaller, and here probably also smaller. So a value that is, but at the end with the max pooling is saying, oh yes, there is an X there. So that is, the feature is there in that corner of the image. The feature is there. So in the smaller figure that we have a number. Yes, there is that feature there. After the next, it will capturing more and more of those things. So that's why the pile becomes more bigger, because there are more richness start growing as you move on the transformation. Another question is the size of the kernels, 3 times 3, 5 times 5, 7 times 7, all that. So the reasoning for what we are doing with 3 times 3 is because the margins are so small. For other examples, an example that we will show you in a minute, they typically use those. I will be using like an evolution of this one, where they have 5 times 5, 7 times 7 in a pile. It's a little bit more complex because it's a residual network that we will use for the pre-train. The point is, okay, this is the common feature. We are chaining max convolution plus max pooling, convolution plus max pooling, final advanced layer, and getting a flatten and getting the output. So this is the idea. I will build this. This is still very, very linear. It's in the sense that we have a layer. So we are just using objects of the instances of COM2D. So in this case, for example, we have 32 kernels in the first. There will be 3 times 3. The activation function at the end, the non-linearity will be given by a ReLU. Remember that yesterday, the ReLU is something that is flat up to 0, and it will return exactly the same name on there. So it's something, you see the derivative is 0 here, it's a constant value. So it's something really, really simple, both for the derivative. It's not, the derivative is not continuous, but this is another. A max pooling, 2 times 2. And after just a flatten, so this will be super simple, just one convolution plus max pooling plus flatten, and giving that to the 10 final outputs with a softmax, the typically function that we use for classification purposes. So you see here what we are doing. Here we have 320 parameters. Those corresponds to the 32 kernels. Each kernel is 3 times 3, so that so we have the max pooling, no parameters with the max pooling. It's just taking on a small reticle grid, 2.2, getting the maximum. And after, when you flatten that, you get this number of parameters. You have 500,000 of parameters. So at the end, this is dominated by that 500,000. This is the number of parameters that we have in this network. I will start feeding this. Yes. So notice that now that I move to convolutional networks, at least in this notebook, I just cut the number of epochs to half just to get this. I was trying several times to run these networks until I get something that runs on the times that allow me to explain those, and at the end getting this. So notice, this is a simple one convolution plus max pooling. Those work like a block. They are typically together. This is 2D because we are dealing with images. If we are dealing with video, it will be a 3D. For example, including the time or the frame numbers. The convolutions could be more complex. Also, if you are, let's say, predicting a flow or something, you will be making slightly different, but they have a collection of those. Yes.
So for the output shape, when we also see the NaN. So what does this NaN means?
Which NaN?
The output shape, yeah, NaN 26, 26, 32. It's summary.
26, 26.
The complex, yeah.
The first element in the tuple is none.
Yeah.
None is the number of elements that you are. So this is just like the shape of the array that it will receive, and the model doesn't know how many samples you will offer.
Okay.
So it's like a non-empty placeholder for this network. Works like this, no matter how many samples you give me. that doesn't matter. So that there is an, let's say, a freedom in the model to receive 10 samples, 60,000. It will receive 60,000, but at this point, when you build the network, you don't have to indicate how many samples you will offer to the model. So those are the 60,000. In this case, we're offering that. So that is what we got this here. So we see here, if you believe me, or you see at the very end, this is much, much better than the previous, the dense layers, the dense neural networks. Still, the accurate, the overfitting is there really soon. So I made 20 epochs, but up to epoch number 5, even less. After epoch, epoch number 5, it did what it can do. Same you can see with the loss. So now, next thing is, okay, I want to cure this a little bit of this explosion of parameters when I move into the dense layer. That's the reason why we are changing from using one convolution plus max pooling into 2 convolutions plus max pooling. So we are making a smaller figures, and with the max pooling is even smaller, we are putting more features, and still, when you build a model, you will see that the number of elements, when you move into the dense layer, goes down. And that's the reason we have 320 parameters. We have, say, 18,000 parameters here for the second section, the second convolution here. But we smash the number of parameters that the inputs that we will get in here for the dense. So this layer is less than half the size of the previous one. And I will be training that. It will take a while. In the middle, I will start talking about the next thing that we will be doing is adding dropouts. Dropouts are kind of like counterintuitive, but there is, again, the idea is having a reason for that. What we have at some point are those networks connected, density connected to everything. The max pooling is saying, okay, for every single iteration, randomly cut some of those connections. So you are pruning the network a little bit. Here, and this one here, say it's 25%, so you are cutting one every 5 steps. And train again. That will give the weights the option to skip from local minimals. Second, it will make the network more resilient. So more connections will be given the opportunity to remember. You are baking some losses, some so like a little bit of loss of memory that allow the system to become more resilient to changes in the system. When you see this here, you will see the effect on, let me see, this one was the adding of the other convolution. You will see that this is better. It's hard to see. This is so simple. But it's still, again, for the validation data, now we are at 99% accuracy. With the dropouts, and here is what I'm doing. I'm pretty much keeping everything the same. Convolution 2D, convolution max pooling. Here, adding a dropout of 25%. By the way, the dropouts only work during training. So that's why when you are running the network, you have to indicate, I am in evaluation mode. The different frameworks use it in different ways. So I'm not training, I am evaluating. The dropouts will have no effect during at that moment. Moving into the dense. So we have, again, a number of parameters here that is reasonable. And it will be running here, it probably will be running here. And when we finish with that, what I'm doing here is summarizing all the 6 networks that I proposed to you in this notebook, the 3 dense and the 3 convolutional, and you will see, and we will learn what is happening with them. Dropouts are very often used. So we will see a few of those in the networks that I will show you in a minute. I will go. Okay. Questions? We got one output image map when we apply one kernel 5 times 5 to the one input image. How are we getting the second and so maps until N1? Oh, the network is just taking this. Let's see. Here. Imagine that we have. Let's put it in the shapes. So the image, the shape of the image, NumPy, will be, let's say, for this case, it's 28. Here, for the kernels, what we will have is, well, it depends on the ordering. So the order, I always confuse with order. It will be 26, 26. So yeah, so it will be 26 times 26 times the number of 32. So why 26? Because we are losing 2 pixels here from this index. From this axis, we are losing 2 pixels. We are losing 2 pixels from this axis, and now we have like a stack. This is 1 for every. Imagine like this. From the point of view of this, we will have here a vector. Is 26, 26, and the final index. The final index, so the final axis will be the number here, a number here, a number here, a number here. 32 numbers. 32 numbers. That correspond to the result for making the convolution with a given kernel. So the kernels are values that are internal to the model, something that is stored in the model. Those are the parameters we change. With this kernel, we apply the image here, and we got this one. We have another kernel here, 3 times 3, that when applied to the image, the 28, in the same corner, for the same set of values, will return me the second value here, the 2 here that way. And we have a pile of those that will produce a vector of those that will be stored in the last x-axis of this 3-dimensional rank 3 tensor. That's how that is. And the model summary. Which model summary, for example, could give you? We will see. Let's see the more complex one. I will try to. The first one. Let's see the first one. So she is asking me, the first one, let's see, the summary. The summary for the convolutional, I imagine. So this one, so let's understand that. The first layer, forget about the input. The input layer is not part of the model. It's not, so the model is flexible. So it receives a number of samples that you want. that is not a problem. So it's the first hidden layer. The first hidden layer will be a convolutional to this. So this is a conv to D. So my representation of that is the network will be like a pile of those things. No, 3 times. Many. Cos plus cos. Yeah. 32 of those. And the corresponding weights. So we have 9 weights here, 9 weights here, 32. The image entered here. Your image entered at this point. It will make the convolution on every single point here. I hope you can see it. I hope the image, and will return here an image that is 2 pixels smaller. After you do the convolution, you play this, you do this many, many times, and you get this image here. This is the map. And you get a pile of maps, solutions. The pile of those maps that will be the use of this kernel, kernel 1, kernel 2, kernel 3. So the use of this kernel 1, that is something that the network will be trained using this kernel here projected on this image. So it will take, see here. So, well, taking the image, projecting here with this kernel of every single section of the image to get this image. This one is 26, 26. This one is 28, 28. These matrices are 3 times 3. We have 32 of those. So we have 32 maps at the end. Those 32 maps, for them, we will be going, well, in this case, we are not doing anything else. We take those maps, all those numbers here, all those numbers. So 32 maps here, 32 maps will be flattened. So all those will be kind of long vector here that will go from this one, this one, this one here that will be collecting all the first section of this one will be 32, 26 times 26, right? 26 times 26. So that will be collecting up to here. I will be making another one for all those points here and here and here and that. I have 26 times 26 for the second one, 3 dots all the way up to the final one. That will be this one that is 26 times 26 that will store here, here, here. So another 26 times 26. So this long vector will go into a dense 100. So we have here a network with 100 that will go into a final here. I have just 10. This is, so we have 100 here, we have 10, and we have a huge thing here. So it's 26, 26, 26, 26, 26, 26, and we have 32 of those. I won't. Are you better in, or I don't want to lose you on the numbers. So let's see the image, or let's put numbers here. 28 times 28. The kernels are 3 times 3. Those are inside the network. Those are the maps. So those are things that are moving forward in the network and that are stored also in the GPU memory, in our case here. So those are 26 times 26. So I will put here 26 times 26 that we will be stretching and sticking. Stretching or that's and it's sticking here. Those we put here, and we have those. We have 32 of those 26 times 26. And is that better? Oh yeah, now the max pooling, and I forgot to insert there. And the max pooling is happening here. So now to alleviate a little bit this, instead of the 26, to alleviate that, we are saying, okay, we have the 26 here. I will be taking this small 2 times 2, getting the maximum number of that, and producing a smaller math that will collect this value, the maximum value observed in this linear code. Now, typically you move, you just not move 1 pixel, you are padding entire to the second, so you move into this one. And you take the sound to take the maximum and you store it here. So this image that was 26 times 26 became reduced to something that is 13 times 13. And we are doing this, so those are the smaller, but the same numbers, we still have 32, but they are smaller. They are half of the size, or quarter of the number of elements. So now when we inject that here, instead of sticking 26 times 26, we're injecting 13 sections, 32 sections of those, 32 blocks of 13 times 13. And that's what you get there. And after you will see the flattening. Now makes sense. Okay, good. Yes?
Is there a theory behind the max pooling, or it's just because to reduce the number of weights that need to be updated? Or there is some...
No, the weights are not reduced. Then,
the author, when he, Alexander, when they think of this, what's in their mind? Why they do this? Just because to reduce the weights, or there's some idea? Like, two
things. Remember what happened when if I don't use the, let me see if I can do it. I can probably do something here just to give you an idea how bad that could be. Let me cut this, and I will be adding this. I will store it here. I will be just experimenting. No, not max pooling, right? So I can build a model and see what happens. See what happens without the max pooling. So now we have 2 million parameters to change. This is one reason. This is a very important reason. So one is that. One is without the max pooling, by the time you move into the dense layer, the number of neurons in these layers will explode incredibly. That's one. Another one is that is a little bit more subtle, is that without the max pooling, the next convolutions will not able to see a more global picture. The max poolings are collecting the data and allow you to see, connecting things that are happening like here with this, with this, with this. So it's allowing you to capture this will be a pattern somehow that will be stored in the when you collect those, you are saying around this region, this pattern is present because we are taking the maximum. So we are saying is there. Pixel plus, pixel minus is around there. Around this location is another thing like that. And now right here is something that looks like this, is something that looks. When you go into the deeper and deeper convolutions, we'll be able to capture this. If you are not using max pooling, you will be stuck in a very narrow section. Will not have this zooming up of looking far away. Imagine that this is like thinking in like you are short sight. So you try to recognize that this is another experiment, that a mental experiment that you can do. Imagine the number. And you put the pixel. And you take a piece of paper, cardboard, and you cut the cardboard in such a way that you only have access to 9 pixels at a time. And you try to see with 9 pixels if this is a 9 or this is what, just looking at 9 pixels. You are allowed to move the cardboard. You are not allowed to remove the cardboard. You try to figure it out what a pixel is just looking at 9 pixels at a time. All that you can do is to record, okay, here I saw a wedge. So maybe this is a 5, maybe 2, because X doesn't have a wedges. A 0 will not have that. So probably, so that will decrease the probability of that being a 0. If you detect in your kernel, if your kernel was optimized with the weights to capture things like this, and you saw that in the figure, you can say that the probability that the number that is behind that image is probably not an 8, it's probably not a 0. Could be a 5, could be a 2, probably not a 1, except that the ones, there are several ways of writing 1. There are several ways of writing 7. You write 7 like this. In Latin America, we learned to write it like this. And those are collected in those sets. So it's able to collect the 7s in many ways of putting those in paper. So that's the idea. 1, decreasing the number of neurons that will go into the lens when you move into that one. And second, being able to zoom out the features and start gathering those. Yes, 25% of the points, yes. So these are the results here, you see here. And the lower 3 you see here, the blue is our initial, green was the second one, no, orange was better. When we move into the green was the deeper dense network, was not, but you see they reach a point where they are not particularly better. It's not, there is a saturation. So now we move into this one, our first network, and first convolutional network here. We got the red points, and now you see, well, it's hard to decide with the MNIST. It's so simple, the MNIST, that it's not so simple to visualize. But there is, if you see in average, there is a tendency to be better when you add dropouts to the net slide. And you see here more evidently, for example, in the losses, that adding dropouts is improving somehow the ability of the network to capture. So I have a few exercises for you here. Probably the time will not allow me to give you that time and try, but I want to move it into things. I want you to do more complex things. And we have only 3 days, so for sure I will not be able to cover the 21 notebooks that I prepared for you. So try one of the things is to decrease the number of neurons rather than adding dropouts. You can try it. That's part of the kind of things that I am asking you in the exercises. Imagine that you want something. What is the minimal network that you can imagine? So the minimal network means which is the network with the lower number of neurons that you can try to produce that give you 95% accuracy with the validation there. So try to be economical. That's one thing. So this is an exploration of that. So I already solved this for you. What happens if I remove the max pooling? You saw that explosion in parameters to 2 million. It will be much harder to train, and it's not justified for such a small problem. Then this is one of the simplest cases you can. So again, and I would like to move you into so that one, this one.
I have one question.
Yes.
In the when you make the networks for the convolution,
Yes.
you also add a ReLU. Where does the ReLU?
The ReLU is I am skipping that bit. The ReLU is
before the max pooling.
Yes, before the max pooling, you put a function that if the number here became negative, you return 0. You store 0. You don't store the negative number, you store 0. So this matrix here, that is 26 and 26, has only positive numbers. Thanks to this, only positive numbers. This one, the max pooling, will be storing the maximal number among tiny sections of 2 times 2. So that is that is where you introduce the non-linearity of this. And that is good and bad. There are positives and bads on that, and there are papers that say, okay, there are better ways of doing that with leaky ReLUs. So really leaky ReLUs, it is. So instead of returning 0, because 0 is kind of a normalizing, or this kind of a blind thing that makes -16 exactly the same as -2, because at the end it will return 0. So this leaky ReLU will take in account that something is really bad or something is not so bad. So they add that, and there are justifications for going into that. And there are some others that say, okay, I would like for some reason to have that sufficiently soft, so something that is a derivative, the derivative is continuous, the derivative is. So there are versions of that try to mix the work between ReLUs and softmax and logistic functions. So they are like soft but going up, something like that. So they look at the very beginning like what you expect from a logistic function, but they don't have the saturation, they just go up. So there are those things. It's in the collection of activation functions that you use. I was skipping for simplicity the activation function. So this is this notebook. Those are try to explore. Again, there is no reason why you cannot try a prime number for the number of kernels. The 31, 19 is just a matter of performance that people select those numbers. So let's move to the next one. Oh, well, you said trial and error. For the selection of the dropouts, you can try trial and error. So I pick 25%. 25%, where I put the dropouts actually here. I put here the dropout 25%. You can try 50, you can try 90 and see what happens. Kernel 1 and kernel 2. What is kernel? What's the difference between? No, they will not be the same. In this paper, if you go into this paper, They will show you, I think they show you, I put the paper here. Let's see. I didn't put the link here. In this another book, in another notebook, I have the link to this paper. So they show you how those maps looks like. They are a little bit like that. One is something like -1, -1, -1, -1, -1, something like this. There are some of those, and they show you the effect of those. Some of those kernels are really good in capturing contours around an image. So they will see a contrast between the background and your image. So
See that online, that's too high.
sorry, what?
The kernel you just drew, if that's too high for them to see online,
Yes, it's
just like off the camera.
it's too high. Okay, but okay. Yes. So let's see. Let's delete this and put this. So you don't have control on that, and that's, let's say, the whole point of deep learning is that you are doing mappings. You are computing pictures without explicitly saying how those pictures looks like. Machine learning, in traditional machine learning, yes, you decide the features that you want to apply. But here is something that is just, the model is learning those things. And say -1, -1, -1. I'm just making a number here. So it could be something like this. And if you apply that figure there, you will get at the end something that just keeps the contour of the figures there. And that's how, for example, those cameras in self-driving vehicles are not only detecting the presence of different entities, and they are capable of making boxes of those things that are moving, detecting, okay, this is a cyclist, this is a pedestrian, this is a dog, this is a signal. All those things is identifying, making the boxes, and all those is just moving pre-trained networks all the time into those systems. Let's move into another notebook because really short on time. And so I will be killing my job here. I will show you why I'm doing this. Let's see if I can get it. Because the two notebooks that I will show you next are pre-trained. Device. I will just change this into let me see this one. We will not be training. So I will be happy just putting without GPUs. Let's do it. Let's do it right. I will be using this one. A standby. 4 hours, 8 cores, no GPUs. And the C Python 310. So any one of those. I just installed the 3 frameworks on all of them. Just select this first. A standby. So that will give me 4 hours. I will be requesting the 4 hours. I will be moving into the CPU 8 cores. Why not? 0 cards, 0 GPU cards, and I will be launching this. And the reason is that I will be using PyTorch. This is a different framework, but I will not be training. I will be using a pre-trained network that will identify images for us. So let's see how this. Any question in the meantime? Okay, I can try to talk in the middle. So I show you in the previous. Oh God, ta-ta. Nate, oh, are you there? It's just me or the machine? It's not working.
These workshops probably really stress the system, right?
We have 58 people. We never have so many participants.
I actually got it yesterday without any issues, was surprising.
I know, so I know. And it's otherwise what I can do. Good. It's what?
It looks like I'm having trouble loading page two. So.
Okay, so I will be going into that, and I will take an inquisitional solution.
Are you restarting the server?
I'm trying to get into the server, but Nate, are you there? No, it's there now. But I'm not able to even log into the machine. Okay. 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 Let's see what I can do.
Can you use the other singularity image to just run a routine train network?
What do you mean? Let's say.
Because you had a notebook running before, right?
Yeah, I have a notebook running, but that notebook was running TensorFlow, and I need to load PyTorch.
But PyTorch is not installed.
PyTorch is not there. Those are images that are specialized and optimized by NVIDIA. So I'm downloading and creating those optimized by NVIDIA for different platforms, for different frameworks. So there is one specialized for TensorFlow. Only TensorFlow is there. Another one is PyTorch. Another was MXNet. So Jupyter notebook. So what I will be trying to do is see if I can use my notebook here and at least show you this. If I, let me see if I can stop sharing here. And I'm sharing. Can you give me
Yeah, hold on.
hold on. Make me co-host in this one so I show this screen.
Yeah. No, I can't, but you might be able to, because I think I made you.
It's me.
Yeah, I'm not able to close my session because I can't get to the dashboard.
Okay. Okay. Are you able to see this? This is on my notebook.
Yeah.
So, okay. So what I will be doing here is, let me see if I can show you this one. Okay, so here I have a pre-trained network. And on PyTorch is really simple. So this one is the paper for the original AlexNet, so the Alex Krzyzewski from the Hinton group, who create the first convolutional network that has an important success in the ImageNet competition in 2012. So you see here that in PyTorch, this is another framework, they offer a list and a collection of models already available. So you don't need to build from zero. You can just take one of those networks. The uppercase versions are just classes, and the lowercase, there are many of those, are just instances of those classes or very particular versions of those networks. And AlexNet is around there in somewhere. AlexNet here on top, the class. So yeah, so I see here that you can create a model with AlexNet. You will see how this network looks like. So you can see the convolutional networks that will pretty much map on what is in the paper. So if you go to the paper, then I probably put the link here for the paper. Yeah, this paper. The paper is there. You can download the PDF if you want. The link is there. So that's not exactly the network that I will be using. But just to tell you, historically, that is one of the big. And you here, I put already offline here. So this is there in the data inside in the folder where we have all the notebooks. I put all the weights pre-trained for that network if you want to use it. But what we'll be doing are other kinds of networks.
It should be back up now.
Oh yeah. Let me see. The question is how. Let's see. It's taking a while, so I will continue here. But if you can try, you can get into the notebook and start executing. So this is another set of like a new class of networks. They are called residual networks. In the meantime, I will be trying to get into that. So Python. Well, we can keep this and try to open the PyTorch. It will be GPU Inter, PyTorch. Let me see if I can go. If I can get it there, I will change there, and so you can see this. Otherwise, I will continue. So these are called residual networks, and ResNet. They won the competition. Oh, yeah, I'm moving to change, presenting what. Oh, yeah, I'm covering you. Sorry. Let's see. Well, I don't know if I can get this. So I will be sharing this one instead. Notebooks. This one. So I will be stop sharing this one. Sharing this one. So I'm moving to this one. I don't know if that's a good idea or not. Well, okay. Are you able to see this more or less? And from those, let me see if I can. Maybe I can do it like this so you can see from far. probably it's better. So this one. Those are pre-trained networks that I will be testing. I was telling you here that this network, was a big success. It brought a lot of attention to the community of visual computer vision. What the network we will be using is a collection of a different network called residual networks that won a competition in 2015. So this was top of the line leading edge research in 2015. And they won a set of competitions with ImageNet. ImageNet is a large data set with images. But what I want to stress here is the number of parameters that those networks have. You have 11 million parameters in this case, up to 60 million parameters. And you can download those weights, all those, they are available to you. So you don't have to start from scratch. You can just take this and use it. In this particular case, I will be, let's see like this. I will be to start running this from the very beginning. To facilitate things, I will skip that. I will not be executing the boxes, but I was taking one particular pre-trained weights for this network. So that is ResNet 101. They have 101 layers in this network. They are a collection of convolutions or max groups. They have connections that made this residual networks work. So I took an image from over the internet. Is this image big? You can see there. So you as a human have no trouble identifying what it is. The point is, can we make a computer to offer an answer to that? So one of the things that we will be doing is reconverting this image into a 228, 228. We make a small image of it. And we are also cropping, normalizing. We are doing something that is needed to be compatible with the way the original network was trained. And usually you need to see the paper for checking what it was used. At the end, you get a tensor that looks like this. So you are converting that into numbers, and the image became something like this. So no longer integers. So the shape, it will be 3 times 224 times 224. The 3 comes from the 3 colors. And you see here, I decompose those in a very naive way. So I took the first section, the reds, the greens, and the blues. So those are the images 224, 224. I am making a batch because for the execution, for the inference of that, they work in batches. So I need to fake a batch. And this faking of a batch is making a batch of one element with the 3 channels, with the 224, 224. That is how PyTorch works. This changes between PyTorch and TensorFlow in the sense that in the batches are always the verified axis, but the channels, in the case if you saw that in the TensorFlow, the channels are always at the end. So there is a flipping here. This is one of the subtleties of one between one another. You can see here the model of that is. Well, it's not so simple. But you can start recognizing things here. Convolutional 2D, max pools. There are some batch normalization. We will see that later. There are residuals. The residuals come from something that is like a convolution 1-1. There are a number of those. It's a long list. It's 101 layers. So you need to really scroll this down to get this done. And remember, I will say they have the table here. This network has the 100, they have 44.5 million weights total. So what I'm doing here is I build this batch and I was inserting that batch into the network, also offering the batch into the net, and it will be answering me with the answer is 1,000 numbers. The 1,000 numbers correspond to 100 categories that were used to identify images. So they use like 18 million or something, I don't remember exactly, million images as training data for this, classified in 1,000 categories. So I have here the text file that will show you, that will give you all those labels. So yeah, so this is a car, this is a cat, this is a dog. It's actually telling you even it's a dog, it's a terrier, it's a Labrador. They have 1,000 different classes for that. And at the end, I am taking the image, checking which is the maximum value on this output. So you see the output, a lot of numbers. I'm just taking the maximum number there. And then seeing to that value, which is the index, and in the list of words, the list of classes, which is the class that corresponds to the index that got the highest probability in the class. So you will see that they got classified that as a box turtle, which it is, with 87.6% of probability. I also showing here which are the other probabilities, because it's not just one. It also has some probability to be something else. And let me see if I can stretch this a little bit. So you see a little bit better this. So box turtle probability 87%. Another one, which is also around the same species, close, a terrapin, a turtle. So it's pretty confident that this is a turtle. And so all the the 5 version is not exactly a turtle, but maybe was confused with the fact that the coloring of the shell, the brightness of that is probably a salamander.
It's like a 0.5%.
Very, yeah, it's a very small percent. So if you capture between the 87, 88, the 3 first, you see, okay, this is doing a good job. By the way, if you see here up here, the tables here, they offer you 2 classifications, 2 lists here. How good it was for that ImageNet collection, the accuracy on the first element. So how good it was identifying correctly the first element, but also what it was, the accuracy, if you are happy with the 5 elements, that the right element was among the first 5. So that is, you see there is a difference here. And those networks, for example, and they get, this is a much harder problem, so they get 82% accuracy. So that's still remarkable. Yeah.
If you go to cell 15, please.
Cell what? Cell 15?
Yeah. So this number means that the deviation where you normalize the picture.
Yes.
Where did you come? Where did you?
Where I made these numbers from?
And if another, for example, if I have another problem, what's this number?
Yeah, for that you have to go. You have to do this. You have to go here to this paper. So you go here and so you open the paper and you tap, and they will tell you, okay, this was what we did to the images. So what they did to the image was a very first like transformation that we normalize the figures that they describe that the figures were normalized. Sometimes they will center, they will crop. So they will tell you what they did. So you have to do the image the same they did, because that was the weights will be depending on the ingredients they use at the very beginning for the preparation of the whole thing. So this is an extra complexity that we don't have here for the digits, because all the digits were first, they have just grayscale, but they were normalized. I think that they normalized that, so the darkest is pure black, and the highest is pure white. So there are some normalization there, and so they are basically taking all those and separating for the 3 different channels, and they probably normalizing that with some standard deviation. So they did some treatment to the image. So it's not just the image to that. So when you go here, the final user, which is me, I'm not offering. I am offering just the image that I download from over internet. The next step will be applying what they use during the training, so the recognition could be as good as possible. Let's say the best possible. So these numbers come from the way the network was trained, and you have to train. And usually, when you go into the page, they will say, "Okay, those were trained with under those and these conditions." And sometimes they offer different versions of those networks, because you can train and get something, but maybe someone could try again with a small change, and they got a better weights with perform better, and so that they put a version 2 there. So you see version 1, version 2. There are 2 versions there, and there is a difference of 3% between one another. So that is where those things come from. And let's move to the next one that I would like to show you. And it's also trained it's also on PyTorch. Still using, yes, the same thing. I will probably try to, I don't know, but the time is so short. I will not run this. You can run it. Then I will just describe what is happening here. So PyTorch, I'm taking the image. And this is from a different paper. So this is I think it's a more recent paper actually. But this is the cover you see. This is a different idea. Those are what it's called a generative adversarial networks. And let me see describe a little bit that, not too deep. So that is the idea. For those, we are using 4 different networks. There is one network here. There's one network here. And there is one network here. There is one network here. And let's see, let's put it like this. So I don't know if I can make this looks correctly. So here I have a generator. This is called a generative. So this network takes images and take images of something and tries to convert it into something else. So it could be, for example, in the cases here, it is general. So it could convert images of horses into zebras. This one, horses to zebras. This one will convert from zebras to horses. Or if you see in the paper, they try with different things, trying to convert photos into pictures in the style of Monet, or summers into winters. So they're trying to convert from one thing into another. So those are the generative networks, and those are the discriminatory networks. So they will say, if this is happy or not with the solution. If they say X looks like a 0, no, it doesn't look like a 0. So it will inform if this network is capable of tricking, be tricked by the conversion. And same here. And those are informing the corresponding network why it was not. It was why it was not so convinced about the transformation. That way, those networks and those go here to here and reconnect here. They will go like in a cycle. That's where the name comes from. So they are cycling between a conversion from one type into another and back. And some networks that tell the system if the conversion was sufficiently convincing or not. So the paper is here. They use a bunch of different variations of the same thing, converting into one photograph into different styles of pictures. Monet, like it looks like a Van Gogh, so that's what we are doing here. We will be taking this network, and here is explicitly shown the network, the convolutions. Let me see if I can. The convolutions and the network here, the generator. So we have here. Here I have this file that is on the folder. You have it on the folder that converts horses into zebras. This is just one portion here of this, because we will be using for us just one of those networks. Forget about those. Those were used for the game. So they are playing a game. They are trying to beat each other into those conversions. We will be taking those. I don't remember the number of parameters on those. This is in the order of millions. And you see here the networks. You need to put the network in evaluation mode, because those networks include, I think, dropouts somewhere. So you need to disable the dropouts. Probably, I don't know if they have something like that. And what I have here is that I download a couple of images from the internet. I downloaded it, so for sure there was those images were not used during the training. Just pick them from Wikipedia or something. So this horse, these horses you see there with the background. So there, it's just not the horse isolated. I put several. So I was trying to make this a little bit trickier. And this one is slightly different. So the horse is very evident that they have this man on top. So what happens with those images? I am processing on the images here. So I'm doing exactly the same, taking the image and creating a batch. So adding an extra axis for the batch, running the network with the first batch, with the second batch, and you see here the output. So you see that they are capable of identifying the zebras, putting the stripes, of identifying the horses, putting the stripes on those horses, and return the image without making a lot of changes to the background. So, and same thing here was, and also the identification of the different body parts of the animal, so to know what should be colored under which way. So the exercise for this is that you can try with the notebook, upload figures. So if you go here, for example, you can upload files. Here you can go, take your image on your computer, upload the figure there, put it somewhere here. What is this giving errors here? Put it somewhere where the network can get. Try to do this exercise. Still treat this like a black box. The point is that you get the image, build the image. This is one thing. Another thing is to create those batches. So you need to fake batch with just one element and do the inference. So run the network on that. So the output in this case, usually how those networks looks like. This is slightly different, significantly different. How those networks work is that you have the image, you have the picture here, pixels, and you are doing some convolutions here. So there is some layers of convolution, and after, at the end, what we have are more is that you are growing. You first squeeze and you after grow until you get a final image. So both your input and your output are images. This is not classification, so we don't have those softmax things. So just a set of convolutions that are trying to capture the elements, and after they are growing and producing a final image. So if you follow this, and I think you can get it here. So what you are having here, you can try to read this, skipping the details that probably not so familiar. You see here, you should start looking at this and start understanding what is happening. So convolutions, ReLUs. So here the activation function is separated here. So another convolution, and ReLU. And now we have another blocks where we are doing more convolutions. And here, and at the end, so we have a bunch of those. And at the end, we have something that are bigger, transforming, and they end up with the final images. So those are a lot of convolutions from the beginning to the end, an image and the input, an image and the output. And you see also the images are not with this of the same size. So they are also slightly reduced, but that's just an effect of the way those networks were trained. So you see there, like the big picture that we use something small, we understood the elements. Now, those, I think this paper is from 2000. I don't put the forgot. I'm sorry. Oh yeah, the paper is here. Oh, I put paper is here. Yes. Yeah, you can see the paper here. So this is very recent. They have different versions of that. I was just using one of those, put the series, just to show you the example. This same technique is used to put faces, so the deep fake device, deep face or something fake or something like that, doing that. So at some point in the future, you will see a video of a politician saying something, and you will never know if that was true or not. So it will be post-true 2.0 or something like that. So everything can be true or false, won, lost. It will be complicated for humanity to deal with the consequences of all this. But it's there. So that is there. What I would like to present is how networks, you can use pre-trained networks. There are ways of accessing this data available over the internet that do those things. And you can use it and just the scale of the problems now. So we use something with 100,000 parameters. Now those things using millions. And the networks that Google, those big tech companies use today, go up to the billion weights today. So they'll go really, really big. So now let's wait for 5 minutes to relax a little bit, and we move into more mathematics, something different. So doing a new iteration on this. 5 minutes, we continue.
So I have a question.
Yes.
So my question is a little bit silly, but it's like, so when we actually load the model from, load the data. So I've seen that like 2 dots then slash. So what is the 2 dots here? So because sometimes I have a problem in loading the model from different file path and
That's because you are not familiar with Linux Unix.
yeah, exactly. That's why.
Let me see here. So in short, the idea is that in Linux systems, 2 dots means the folder that is on top.
Okay. The folder I'm in right now.
The folder that you are right now is dot.
Dot.
That you say dot. It's just so you see here this. My account, for example, in the system is users, Franco, and let's say that we have here learning, and after after we have the notebooks. Let me put this way. Everything in Unix start with a slash.
Okay.
There are several folders here.
Okay.
One of those folders is called users. There are many folders here. One of those folders is Franco. There are many folders here. One of those is learning. There are a few folders here. There is, for example, one called data. There is another called notebooks. Books. Right?
Yeah.
And here we have the different chapter 1, chapter 2.
Chapter 2. Yeah.
So we are working in chapter 2C something.
Yeah.
So this is the notebook.
Yes.
This is the notebook.
Okay.
When you see dots, is the folder where you are.
So 1 dot or 2 dot?
1 dot.
Okay.
1 dot is the folder where you are.
Okay.
Where the folder where this notebook is. Okay. 2 dots will be the folder up. So if this one is here, 2 dots will go to this one. So I am moving one folder up. I'm looking for the data, and inside this one, there are many files. One of those files is the deep learning. So, well, actually here I'm in Scratch. So it will be instead of users, so it's Scratch.
Yeah, I got your point.
Scratch. So notebooks, and here you have 1C, one. So we're folded up will be deep learning, and after you go into data, and here I put the horses to Zebra PTH. This is for the PyTorch. It's 45 megabytes. All those are all the weights. So there are millions of weights there. I think it's a pickle file. So it's a way of storing a large number of data. I don't know. Probably it's storing all those numbers as arrays. So when you load them, you will get in all those the model is taking, it's probably dictionary, so they take, okay, which are the dictionary of all the NumPy arrays corresponding to the first convolution, the first layer of convolution. So this pile, notice the, for example, the ResNet. Remember that the ResNet has 101 layers. Some of them are at max pool, so they don't have parameters, but some of them are convolutions. So they are pile of kernels, the kernels that succeed training this. So all those arrays, it will be one of the things that is taken and is offering to the model, okay, use this for the second layer. So use this. We'll put all those in place. So the next time they get the image, the only image Lord is doing is traversing all those convolutions, doing all those convolutions again. Super easy. So a cell phone is doing that all the time. So if you have those things in the cell phone that recognize images, it's super easy for a cell phone. You don't need much because all that is doing is taking pre-trained data, printed in weights, traversing with the image through the whole network and offering the results. The hard part is what they do with the GPUs, what we are doing with the GPUs, that is training the network because it's changing all these parameters. But going back to your question, yes, is the way we understand in Unix systems the location of orders relative to
So I have another question.
Yeah.
So the question is like, so when I did the training the model, sometimes when you run it twice in the notebook, run it twice. So I trained the model first, and then again without restarting the kernel. When we run it again, the layers names are changed. When previously it was like dance layer 1, dance layer 2. Then, how to actually get rid of that things? Because
yes, there is one way. I think I use it in another notebook. Are you using PyTorch or?
I'm using TensorFlow.
TensorFlow, okay. It's with Keras. So the idea is that Keras has some like a clerical management of the objects in that you are working with. So and they will assign names to the different things. Those are objects. So by default, they will collect all that and they will start putting dense one, this, that. You can name every single layer on those things. So you can say, okay, this layer will be called this way, and you can refer it with the name. So in one notebook, I think I make an example of naming the layers so they don't change. This is one thing. Another thing that you can do is that you can reset the environment. So forget about all that. I will
restart the kernel.
Yeah, let's say, throw away your accounting book of objects. So forget about all that. I will start. So it will clean. I will save some memory again because it's just the definition. So that is not too much. But it's just the naming. The naming will change and all that. But you can both rename and also clean your environment somehow.
So if I clean the environment, so I have to train the model again, isn't it?
No. It's just the naming of the layers. So the layers you will have something like you can put the name. So you are working with a dense layer. So I will call this my dense 1 or dense first. So you put names to that. It's just the fact that for the next layer, even you are not using this anymore, the names will change.
Yeah.
But that's one thing. Another thing is to create a network. And once you create a network, you can inject the parameters that were trained. Or for example, if you trained before and you are in a process of training, and so you got something that was good, but you want to train more, you want to explore it more, you import those weights and you start from there. You don't start all over again from the scratch.
Yeah, exactly.
So you don't want to do that. And I will show you probably this afternoon. It's something that I will discuss with you in a minute, what I will do, because I'm really short on time.
Yeah, I got it.
I want to do more things. I want to show you more complex things. But I don't want you to feel behind, so I'm making a balance. It all depends if you pose questions or not. I want you to learn, no grades, so this is your opportunity for learning things. I'm not sure if I'll show the machine learning or I will continue with the deep learning stuff this afternoon. But yes, in one of those notebooks, I am, for example, training for a few epochs, storing that in a file, recovering those wakes from the file and continue. And you will see it was good, the losses are going down, you store, or you record, and you continue and succeed. Especially if you are training, for example, for more than a week.
Yeah,
you
exactly.
You are constrained by 1 week in our cluster. If you don't own the nodes,
Yeah, exactly.
the community nodes are limited to just 1 week. So you can train for 6 days, store that, or make checkpoints permanently with the best network that you got. And after that, you can continue. That's it. Yeah. And you can say, okay, this time I will continue, but I will add the dropout or lower the dropout. Let's see if I get better. I keep those. I explore different venues. So this is something more elaborate. Eventually, someone asked me about, let's say, using the cluster for deep learning. This is for learning, for us learning. But when you are doing this for real, for research, what you want to do is not running notebooks, is having a Python script and creating a submission script that we submit the job to the cluster, maybe several of those jobs to the cluster, and you will run those for days, and you get the data.
So it's better to actually run the, .py file rather than the IPN, right? In the clusters.
Oh yes, this is for learning purposes, for us learning purposes.
Okay.
But because you are doing interactive.
So is it possible? Today or tomorrow, like for a small portion, like how to just directly run the .py script in
a terminal. So you need, but for that you need more confidence with command line, because the command line is not on Jupyter Notebook. But yes, that's what you want to do at the end. So this is just motivating you into the deep learning area, and I will show you that. Probably now that you raised that point, I will probably show that with a very simple example.
Simple example.
The next simple example with them is how you take the portions that you need to make a script, a Python script that will go into the cluster. You submit the job, and when the job is done, you will get the weights, you will get everything, and you can present, okay, I have a network that do this.
So then after the training of that model, we can take the model from the cluster and use it in our local computer, isn't it? Like for the testing purpose.
For inference.
For the inference,
yes, you can take it. You can take it
from the cluster.
Yeah, I was using my computer. So here I had the data. My computer doesn't have a particularly, well, it has a good GPU, but it was not an NVIDIA GPU. This is a Mac. And I can use it. It works. After you have that, you can put in a cell phone, you can put in a Raspberry, you can put in a drone.
So it's a full-fledged implication.
Yes. This thing is used to kill people in other countries.
Thank you.
Let's move on to something else. Let's see here. Probably we'll go back here, no GPU, because I would like to go back and do some math. I hope you got excited with the thing. So now math is also excited, but in a different way. So I will be launching this. I don't stand by. The question, use the audio files. Yes, audio files, but not with convolutional networks, with something else. Audio files, so you mean streams, so you mean signals, So time series, the kind of networks that we use there are different. Are called recurrent networks. I hope I can show you something like that tomorrow. We will see. We will see. But those are for those. Yes, you can use those for something else than an image. Also, you can use that for things that have nothing to do with images, like a bunch of parameters. If you are, let's say, a bank or something trying to offer a loan or someone else, you can inspect a lot of parameters. So you don't want to use the photo of the person to decide if you offer a mortgage or not, because you will see with the bias of some countries and racism what it will end up with it. You use all the data, or you try to still all the things, not just images. Go here, and number of GPU cards are 0. I will not be using GPUs. Okay. Probably will free this one. Let's see. So yesterday in the afternoon, we saw this. Let me see if I go into this one. Well, this could be one. Well, let's go into this way. Things change topics a little bit. That means that. Okay, so what I have in the next 3 notebooks, and I will try to cover those in the 30 minutes that we have left, is how the different frameworks generalizes the idea of NumPy arrays. So all those notebooks, all those frameworks, they have support for several languages. First, you are by no means feel attached to just doing this with Python. There are ways of doing this with R. For example, if you're familiar with R, there are APIs for those languages too. Java, for example, is another one, or directly for production things in C, C++. But in the case of Python, the standard de facto for everything that is numerical is NumPy. But NumPy has a limitation of storing those arrays only on the CPU RAM, the normal memory of the computer. But in many cases, those neural networks are trained on GPUs. The GPU is a separate completely, so you have here CPU, and a CPU has its own memory. The GPU is a different card that has a lot of tiny dummy cores that have nothing to do with the CPU cores. They're not capable of the same thing but they are capable of doing dummy things many times. And those are attached to its own memory. When you are working with NumPy, you can only allocate objects here in this memory, CPU memory. What we are doing here is that every of those frameworks have creative ways to use the same ideas that we have with NumPy with another object that allow you to move data into the GPU. In the case, in the meantime, I will be doing something else because I will show you the difference here. I will create another with PyTorch with one GPU. PyTorch. Okay. Wait a second. So this one is how PyTorch, which is one of the three frameworks. Remember, the three frameworks today, 95% of the work in deep learning is done in those three networks: TensorFlow, PyTorch, and MXNet. They have a way of storing those and creating tensors of that. So let's start with executing this and notebook. Let's clean this. Let's start cleaning the output of this notebook. PyTorch tensors. So you can start with this. Those are Python list and Python tuples. With a tuple I mentioned yesterday in the afternoon, this is just remembering for those who feel comfortable with Python yesterday, that you can take lists and attach elements. So you can create NumPy arrays, all of them, and they change in something like this. You can only have one type, and that's, let's say, the condition of that. They are stored in a different way, and when you operate with those, NumPy is supported by two libraries, BLAS or LAPACK. Those libraries were created in the 70s. So they were written originally in Fortran 77, were old. They are extremely efficient, and people over time have improved those with various techniques. Some of them really genius ways of doing linear algebra operations very efficiently. BLAS is just basic operations, linear algebra, matrix multiplication, matrix vector all the time. LAPACK means the decompositions, inversions, eigenvalues, eigenvectors, that sort of thing in linear algebra. And some of those versions of that are optimized to be multi-threaded, so they can take a machine, a CPU, with 4 cores and take advantage of that. One of that you can think is if you have a long vector and you are computing a dot product of those very long vectors, which is something that you do all the time, it's very tall vector. So you can cut those vectors in 4 as one core to compute the dot product of that, and at the end you just sum the result. So that there is one thing. Typically, you would want to use a multi-threaded version of that. There are a few well-known today, or widely used. One is OpenBLAS. Another one is the MKL, which is the Intel optimized version of those libraries. And still, the limitation for NumPy is that it can only operate on CPUs. Moving to the GPU, the people behind PyTorch create its own objects, similar to those in NumPy. Let me see if I can go here. I probably did a mistake. Yes, I know what it is. Stand by. So that goes into how you determine if you are in a machine with a GPU. One way is to execute this command. You get nothing. It's because you don't have a GPU. This is from the command line. If you are on a terminal, I am just showing you this from a notebook. From a terminal, how you know if you have access to a GPU. This is one. From PyTorch, you execute this. There is torch. You load torch, and you say torch CUDA is available. You are calling this method, which will answer with true or false if the GPU is available. And if it's available, you can also request or work in infer or in another way how many GPUs are there. So you can use GPU 0, 1, 2, they have numbers for that. And I'm trying to get this to show you the difference when you are on a machine with GPUs. Okay, so I will be cleaning this. This is the answer that you get when you are running a GPU. It will tell you this is a command that is part of the NVIDIA CUDA toolkit. So when you have a machine with a GPU, if you are a gamer, you have a good machine, and if you want to explore a little bit this, some machine, you install the CUDA NVIDIA toolkit. Use something that you can download for free or from NVIDIA webpage. The current version is 11.6, 11.7. I don't remember very well. 11.7. I think this is the latest version. And it will tell you the GPU. In this case, I got the original version, the original GPU that we got for this cluster. They were Quadro P6000. You see here, this machine has 24 gigabytes of GPU RAM. And they are currently doing nothing. They also inform about the energy. You see, this consumes up to 250 watts. So that's another thing. They consume an important amount of energy. That means that they produce a lot of heat that you need to dissipate, either with a combination of air and reticula, aluminum, things like that. And now you get something like this. When you execute, you get, yes, I'm using a CUDA device. That means that you can create arrays, and you will see those, that you can move into a GPU. You can transfer. There is nothing, the GPUs cannot work with this memory. The CPU cannot work with this memory. You need an explicit copy of the data from the CPU to the GPU. Yeah. This is, I know what it is. This is because I need to kill one. This one. And I need to probably kill this.
How to kill without it? That's
How to what? Sorry? Could you repeat this?
How to terminate?
Oh, there's several ways. I was doing it in a very crude way, closing the tab. But here, if you go here, you can see the kernels that are running. So you
how to terminate the session from the cluster.
Oh, the session of the cluster. You see here. You go here to the list of sessions or the list of and you hit delete. And you just close that session. That was the reason why I got the message, because I have the same notebook open with two different ways, and one was changing, trying to save, and checking that the other was that the notebook was changed. So now I'm using the CUDA, and now we will start learning how to create those arrays, those tensors. That's the terminology, which is slightly different or significantly different with the understanding of a tensor in physics and mathematics. But that's what we call them. So tensor for us, tensor is just a multidimensional array of numbers. There is not covariant, contravariant, no, there is nothing. Just a range of numbers with some dimensions does a tensor. So we are able to create 5 times 5 random empty. It means reload. It will be when you create an empty array, it's not 0 because this memory has been used. And so when you are creating an array, and it's here in the second, when you are creating an array that's empty, it's just picking the garbage that was there. In that. There you see big numbers, small numbers, they have no meaning at all, which is different from creating an array from 0. So it's taking this and initializing the values with 0. And random here. This is how you create a tensor 3 times 3 with integers, random integers. So all those are the basic blocks, the building blocks of tensor, which are the main ingredient of neural networks. So here I am creating one. You can get values, specific values with indexing. You can take a list of lists to build a multidimensional tensor. So pretty much exactly the same as NumPy. To this point, I think it's bit by bit exactly what you do with NumPy. Now, here, okay, and one of the things is that those things have D types. So the data type associated to that array. In PyTorch, those are instances here of those things, of those classes. Torch integer 8 bits. You can reshape, something that also we can do on NumPy. So up to here, I think it's exactly the same. Yes, and here is a list of the names in PyTorch for the different data types that you can put data. I think the default is integer 32 and floats for real numbers. So there is one default, and you can change that if you want to. Yeah, there is the default. And so you can take one tensor and ask what's the data type for that. You can take that and create a new, remember, again, with NumPy arrays, when you have an array, you cannot change the shape, let's say, but you cannot add elements, and you cannot take integers and convert them into floating point numbers. What you can do is create a new one with a changed version of the data type. Now, that's what I'm doing here. So, but you can see, same as I showed you yesterday for the NumPy, for the Python session, that there is concepts here. So let me see, I will edit this. That those things, regardless of how they are, if they are matrices or vectors or they have rank 3 tensors, rank 4 tensors, whatever, they are stored as a long list of numbers, usually continuous, stored in memory this way. And this is the way of accessing those elements. There is another way, but this is a more Python thing, that you can ask, for example, where is the location in memory? So for addressing those things, I skip that, but so all those numbers here are stored this way as just a long string. And when you ask for the storage, they will also tell you on which device that memory is allocated, because now you can store that also on the GPU, the data type, all that. So what I'm doing here, there are a few operations that you can do in place. So you can change values. The values are okay to change, so you can fill them. And this is probably the most important lesson, and it's very evident for maybe I have the figure. Yeah, I have the figure for that, so I don't have to draw it. And so a tensor has some elements. So this is the way this is stored. But internal, the tensor offers a few other elements here. The shape, stripe, you see that in the figure. There are the ways how you can access the elements of those tensors. So here I'm creating a tensor 11, 17, 1. So it's an array, so from 11 up to 17 is jump from 1. I reshape that. So when I reshape, I'm not getting a new array. I am just transforming the way I present that array into a matrix. 3 rows, 2 columns, if you want to think it that way. And you see here how they are stored. I actually put this. So now let's go into those 3 elements. There are the internal machinery of how PyTorch tensors are stored. One is the shape, another is the stripe, another is the offset. In this case, I am showing you the shape, the stripe, and the shape. Here is 3 times 2. The stripe is 2 times 1. What is the meaning of a stripe? Is how many jumps you need to do if you change columns without changing rows. When you change in one of the axes, keeping the other axis unchanged. You see here for 13 to 14, we are changing the column, but we are not changing the row. We're on the same row, just changing the column. What is the change we are doing? We are moving one portion of the memory for whatever is the data type of this. It is 4 bytes. It's Intel 64, so it's 64 bits. So it's shifting 64 bits to get the next integer. That's one shift. So the strike is 1 to the next column. And what is the movement that you have to do? If you are jumping from one column, from one row to the next row without changing columns. So this is the example that I'm putting here from 12 to 14. You move from this one to this one. You move 2 blocks. That is what the tensor is actually storing. It's storing the shape, it's storing the stripe. We will use the offset right now. The offset in this case is 0. But when you make views of those tensors, the shifting could change. You will see that in a minute. And the idea is that idea of keeping just the stripe and the shape allow you to transpose matrices without changing anything in memory. So the memory for the matrix is exactly the same in the same location, but you transport them. And transposing is fundamental to many things in linear algebra. So you don't want to take 1,000,000 times 1,000,000 values and transpose that and put that in a copy on another location. So the transposition here is taking all those values. You see here how they look like. What is broken? Oh, I don't know. Well, so notice that I have exactly the same values. 11, 12, 13, blah, blah. The matrix now has a different shape. Compare this 3, 2, I transpose to 3. but the stride have been inverted. So here is 2, 1, and here is 1, 3. What is the meaning of that stride? Is that to change rows, we just move 1 jump. To change columns, without changing rows, now they just move 2. And that way you get exactly the same, or you get the transpose of the matrix without changing values. That is one of the important things here. Here I'm doing something else. I am adding another view, B, which is taking just 11, 12, and 13. And so it's taking from this matrix, I am keeping the first row and the last row, just to show you how that looks like. So the memory is the same. So the storage is exactly the same. We are not changing the storage. Contain exactly. If you ask for the location in memory, it's exactly the same location in memory. The shape now is 2, 3. The stride has changed into 6, 1. What is the meaning now? For moving into this one, from one element to the same element, to changing rows without changing columns, you now need to move 1, 2, 3, 4, 5, 6. That's why the stride is 6. To change columns, you just move by 1. So that is the internal way of understanding those things work. Now I'm making another section. This is one of the corner of that. You see how this could be important, because when we are doing convolutions, and we saw all those convolutions before, this is what you are actually doing. You are taking a portion of the image, and that portion of the image is just putting the indexes in the right way, taking the image of the kernel, making the sum, and NumPy, these kind of things, we'll do that in one call. We'll do the sum, take the sum of the, do the multiplication, sorry, element by element, do the multiplication, taking the sum, and return the value. So we are all doing, and after we move, and the moving is just in a stride, it's just shifting the value. We are not creating new arrays all the time. They will be very inefficient if we work that way. So that is the stride, for example, in this case, and put another example where I'm just trying the movements in one direction is 3 in the columns as well. And so I told you that in many cases, those things were not created contiguous, but with those manipulations, they could not. So this one, for example, A, when I create A, is contiguous in memory. When I create B, B is being that the elements will not follow that. And sometimes you need those to be contiguous. This is kind of a more advanced thing. And that continuity can be granted or can be converted on the fly when it's needed. So you can take a vector and make it contiguous. If that is why at that moment, yes, you will be making some copies. So there are some memory movement there. So the final point for you is knowing that you are trying to make all those operations, all those convolutions with the minimal moments of memory possible, because that is where efficient comes from. So here I have the shape. I am here making some of those operations. So they start looking here. They have the sum, so element by element. There are another way of doing that. You can explicitly call the method add to the object tensor torch. And now there's another way where you are overloading, you are taking the element X, or those with underscore are changes in place. So you take Y, you add X, and you're storing in Y. So those are changing in place. There are several of those functions. The difference between this one and this one is that this one returns a new tensor. This one will overimpose the previous one. Same thing here, what I'm doing here into Python. what I'm doing. Okay, I can take the one particular item. When you take one particular, let's say, you index this way, y is still a tensor. It's a tensor with just one number. So for some things, you cannot operate that like that because the tensor is not a number. For Python, it's an object, it's another thing. So you can take the item and it will basically undress the object and just return the pure Python object will be 70. Or you can convert those into a list. And so there is that capability to convert it. So this section is converting into Python objects, basic Python objects. But something more interesting than that is converting those things from PyTorch tensors into NumPy arrays. And it's also this is also transparent. If by chance this tensor is in the GPU, so it's allocated in the GPU, when you convert it into NumPy, you will be bringing the data into CPU, making the NumPy array and return. Otherwise, it will be returning the object in the same location of memory, so no copies are done. So they have the two behaviors, which is a smart thing to do when depending on is in GPU or in CPU memory. So that is one example I'm doing here is taking one of the elements, I'm putting 999, and you notice that Y have changed because it's actually the same location in memory. So now moving into the GPU, I can create tensors directly in the GPU. This is something that I can do here because I'm running this notebook. At the beginning, it's a bit slow. And by the way, comparing with internal CPU memory movements, moving data into the GPU is expensive. Moving data from the GPU to the main memory is expensive. You want to minimize that. So all the operations, and you try to keep the memory in the GPU as much as you can and do all those operations. You don't want to bring that data back and forth from the GPU to the CPU. So here what I'm doing is asking to move the data to the GPU. There are several ways of doing that. You can initialize like this, or you can, and I put this so this notebook will work even if you are not using a GPU. It will just skip that entirely. And this is, those are ways of moving data that is in the GPU to the CPU or vice versa. And some serialization things happening here. Serialization means getting the data in a way that I can store it in a file and I can recover it. And so here I have an array. Here I am saving an array. This goes into the idea, okay, I got my network training. So I have all those weights, all those biases, all that. I would like to store that. All those weights and biases are PyTorch tensors. And this is one way. There are more sophisticated ways, more particular for the neural networks. But at the end, this is what it's doing, is storing those tensors in a certain format here. And you can, again, load from the file and recover the content of those tensors. This is one way of doing things. A better way of doing this is using an external library. HDF5 is a standard that was created originally, I think I don't know if it's NOAA or I think it was here in the United States. For the purpose of storing large amount of meteorological data. So this is an important problem for them. This is a standard. I forgot to install HDF5. This is my fault. I don't have HDF5 on this particular Singularity container. It is in the And by the way, this is on it, so I will have to skip this section, let's say, not executing the mods. HDFI allow you to store big matrices or a lot of data in binary format. This is a good thing. It's very inefficient in storing numbers, a lot of numbers, as text files. Though there's these crazy people who store hundreds of thousands of data in CSV files and hope for the best that you can load that efficiently. That will not happen when you have millions of files of numbers. So HDFI first is storing the data in a binary format. Second, it allows you to store in hierarchical ways, like a tree. So you have this data that is a big range of numbers that mean this, and also you can store metadata there. So those are the temperatures of my experiment. Those are the pressures, and I have a matrix of pressures, a matrix of temperatures, a matrix of this and this and that. So the next time you don't need to figure it out, but what the hell are you storing in this array? They have the numbers, and I don't know, except if I have an extra file when they say readme, and they say the first column is this, the second column is this or that. You solve all that with HDFI. It's very efficient. It's a standard. So many libraries store those things. I cannot execute those boxes there. And I move into this. It will be quick because we will go back into this autograd problem for some of it. But I will give you the general idea why we have that. Tensors could also have the possibility of storing more than themselves. You can store the gradients. So when you are doing this, and we will see a little bit of this from the mathematical point of view, not from the computational, from the mathematical point of view, you are running a network. You have a network here. And this network looks like this. And it's a dense connected network. So you have all those points connected to everywhere. Making this right. When you are back propagating, you are keeping this. So you can think on top of each link here, there is a W. This is the W connecting this with this. This is actually here. This is part of this neuron. But it's another way of putting it is on top of each link, edge here in those. So those are here all the weights. And all those weights change with the derivatives of them, partial derivatives of them, keeping everything else constant. So when you are running those networks, you want to store all those derivatives because they are reused many times during backpropagation. You are basically asking the question, what is the change that I have here when I change something here? When I'm changing something here will depend on this connection that will go later into this connection. So when I think here, so this connection is needed, this connection is needed, this connection is needed, this connection is needed. If I am asking what is the partial derivative versus something happening versus the input here. So something here. So it will be like it's a sum on all the paths that you have to do to reach into this point. So for that, you need to store all those partial derivatives here, in those places, and that is what autograd is doing, storing all those numerical derivatives. So you can request for a tensor to keep track of those gradients. That is something that also NumPy doesn't offer. So this is another reason for extending NumPy into something that offers gradients. So now I am adding a sum. I am computing the sum, and so it's taking care of what is happening there. It's keeping all that and making here how that looks. And later you can compute the gradients. Let me see if I could skip something. No, it's okay.
So why dot grad func is like it's a function to calculate the gradient up to that point.
Which one? Sorry.
The next 98.
Yes. Yes, this is a function. Stop that. It will give me just the return of the function. What I'm doing here is that I took an array once, I did one operation, and now I am computing the gradients, and I'm seeing what is. Oh, screw this. This is probably better when we return into this, hopefully this afternoon, I think, into this from the mathematical point of view, from the it will be returning to me the numerical gradients in those locations, and so they are storing all that. Those things change and they are reused. So you need a way of storing. So I have here some exercises for you. The time is so short that I will not be able to give you time for them, and we are hitting the noon at this point. Some of them is just for you to familiarize with those manipulations, especially put some emphasis on you to understand the shape, the stride, all this, the offset, that because those things, even if those things happen transparent to you, it's important that you keep in your background, in your back of your memory, those things that are happening when you are training neural networks. Okay. So here there is another one doing that. What I'm proposing is that this afternoon I would probably have to change my mind on what I was expecting. What about if I skip the machine learning part, or probably just mention very, very briefly, or for you to keep an eye on this, especially this one, the iris. What I'm doing here is just was expecting for this afternoon being just pure machine learning. What I'm doing here is taking one example, a very classical example of machine learning, that is not necessarily for you for deep learning to understand, but it's good to have a feeling what is after deep learning. What is deep learning is embedded in something bigger that is called machine learning. And so here I was using one case that is called the Anderson iris data set that was created by a guy name. Was working for another guy with a very dubious racial considerations, but that's history. And he was trying, let's say, to justify why Black people are less intelligent. Some of that history have moved on. And from that, from ideas in eugenics, that they came with this example for flowers, trying to identify flowers. The point is that I was playing with this in different methods for machine learning. So logistic regression, for those who are not familiar with that, pay attention to have a look at this. The logistic regression, ways of classifying the three kinds of flowers. So those are three kinds of flowers, and we have 4 parameters for them. So they are measuring for the flowers, the petals, the sepals, and there is one classification method that is called logistic regression. There is another classification method that is called logistic support vector machines that are right here. Networks support vector machines, which is basically creating like stripes that maximize the width of the avenue, and perceptrons. perceptron. This is another method that was used, and this is like the grandfather of neural networks, the perceptron. I mentioned that during the first one session. So I use a perceptron to solve the problem of classification of these flowers. So get a line that separates them with an iterative method. I also here showing other things beyond that, the classical PCA, where you are trying to find the dimensions that are captured most of the values of that. So that it will take me like a couple of hours describing a little bit, even a little bit of that. And I have another example that is the even or tiny 8 times 8 digits solved with some other methods, Bayes methods. So, and the idea of Bayes theory and the confusion matrix. So I have a few things that are interesting, but if I devote this next 2 hours in the afternoon to machine learning, I will probably not have enough time for showing some more advanced stuff yesterday. So I probably will do the sacrifice on machine learning for the afternoon, skipping this and moving into the other methods of storing tensors and the mathematics behind deep learning. So tomorrow we will do more advanced things with convolutional networks, understanding about the storing the data, storing the partial results, doing checkpointing, all that. So we will return at 2 o'clock, and we will be continue with neural networks. So from the mathematical point of view, and the perceptron will come back again. So I have one notebook. When I develop the perceptron entirely, I train the perceptron entirely. So this will give you a feeling of a simplified version of what a neural network is doing when you don't have the hidden layers, which simplify things. So thank you very much. We return at 2 o'clock for more deep learning. So
And we're still going to have access to these notebooks.
Yes.
After the workshop.
can you hear me? Can you hear me? Hello? Yeah. Okay. So the next notebooks that we will be working on, we can work those with this one, C Python 3.10.5. And so go to Open Math as usual. See. And Jupyter Notebook, and select here C Python 3.10.5. And yeah, we don't need GPUs for this thing. So we can select just standby, it will be fine. And we'll request 4 hours. for a course, let's say for course, we have 38 people right now, 3 people here. No GPUs, so 0 GPUs, and Jupyter, and that's it. So I will show you again. CPython 310, standby, 4 hours, 4 CPUs, no GPUs, 0 GPUs, no other option is relevant here, and you hit launch. Connect to Jupyter. Scratch. Deep learning. Notebooks. So what I will be doing is I will just show you this notebook really quickly, so you get an idea of what you can learn from it by your own, because I would like to concentrate my efforts on a couple of other notebooks more target to neural networks. So this one is a general overview of the area of machine learning. The purpose here is for you to understand what it is, the idea of learning from data, finding patterns. We mentioned that a little bit here. The idea how traditional scientific programming works, and the idea how machine learning approaches the same problem, those problems with data, learning from data. Here I'm making a description. This is something that you find easily on internet, how the classification, the traditional classification for machine learning algorithms as supervised, unsupervised, reinforcement learning. And so there are a few examples here that I don't have time to. So I would like to focus more specifically on deep learning. So I will just mention here briefly that I have some notebooks here, a couple of notebooks where I am using scikit-learn, which is another library for machine learning on Python, where I'm doing some examples of classification under several methods for classifying numbers, discussing the ideas of classifiers, outliers, Bayes methods, anomaly detection, so how some algorithms work with that. The principal component analysis, which will devote me some time, it will go into that. If you want a graphical idea behind that, is to try to find a direction, so something with a lower dimensionality that is trying to maximize the amount of information that you want to keep from the system. So the idea is that the PCA will try to find this line that connects the purple ones, and at that moment you are spraying maximum the points, so you're getting the maximum direction where you are getting the direction where you are getting the maximum information from the system. So clustering methods, so there are some images, how those methods work. They're relatively simple to understand. The idea of trying to find centers of mass and displacing those centers of mass as you find more and more elements that are closer to this one than any other value. So that is the idea behind these clustering methods. There are a bunch of methods related to this. The idea of loss function, which is also related to deep learning. So, but we manage that more specifically, the idea of the cross entropy loss, and a few other topics. And at some point, I think, here. So this is an overview. You can do it on your own. I would like to skip this one. And also would like to skip this one. I will just show you very briefly what it is. It's a data set that has like, I think it's 150, 50 samples of the measurements done on flowers. So a total of 150 instances where you are measuring 4 values. So you have 4 columns of data, and you are trying to create a method that uses the data to identify which flower is which, or a particular flower with some measurements, or to which of those 3 versions, three species belong. I was using some methods, and some of them, one of them is a logistic regression, which is a classification method that uses a very simple formula to separate 2 areas with a line in principle, and make that separation. So dividing the points into the 2 sections. This is 1 point that could be extended with some nonlinearity, and the k nearest neighbors, which is something that is learning which is the area that belongs to each point. We are talking about 4 dimensions, so what you see here are projections of just 2 of those variables, but in fact what you have is a 4-dimensional problem. So with that, you are identify which is the region that belongs to each kind of flower, the 3 species of flowers. Based on that, the support vector machines that basically tries to separate the areas by creating some avenues. Here they don't have this, but here there's some separations that maximizes the venues among those points. Those are called the support vectors. What I would like to introduce here, which will be my entrance point for the next notebook, is the idea of perceptrons. Perceptrons, you will see, are very, very simple entities that basically have some weights, as we discussed for the neural networks. Those weights are multiplied by the x's, so the input vector, and you take the sum, you take the product of all those weights and x, and you make the sum at the end, and you try to optimize or modify the values, the weights, in such a way that you can classify the elements for the 2 species, of those flowers. So that is, and in this case, yes, it's like a single layer perceptron, a neural network with no hidden layers. And this is what I'm showing here, that through an iterative process where you are introducing all those points in the system, the system is learning which are the weights that will eventually fulfill the role of separating those points in 2 different areas. So that is what is on here. And also showing a few other topics also in machine learning, like dimensionality reduction. So I talk a little bit about that. So how you separate that with some venues, and a small example of how little digits. This is an example from an era before deep learning. And so you see, you need to look at those from far away to identify what they are. And one concept that we will not enter too much detail is those, and there are 4 values that you want to pay attention when you are doing this kind of stuff. Is pay attention to the accuracy. Something usually you always mention the accuracy because the kind of problem that we have, the kind of samples that we have are such that are so well balanced, so perfectly balanced, where such as that the accuracy is a good metric for us. And sometimes you need to go into something else, like the precision, with the number of positives that you have divided by the number of true positives plus the false positives. So you give you a different balance of your model. Remember what I mentioned to you, one place in my country where it rains 360 days a year. So a model that is predicting rain every single day will have a high accuracy. But those other values will not be set, will not be represented that way. So by the way, every single time that it doesn't rain, well, will be counted as a false positive. So at the end, what you get is something that is called a confusion matrix that put all those values in a single table. I don't know if I have it here, but typically you produce a table that those values. And the idea of cross-validation, I will not go into this. I will skip it so I could enter more directly into the neural networks. But keep in mind that if you want to fill some gaps on things that I mentioned closer to machine learning, you can find a little bit of information here. So what I would like to jump is into this one. I will devote some time to see one example of what it is, the precursor of a neural network. It will help us to understand some of the things that happen when we introduce hidden layers. So this one I will be running and explain a little bit. A perceptron is what I mentioned, is like the grandfather or the father of neural networks, and the grandfather of deep neural networks. You will see why. For this, I will be using basically NumPy. I was using pandas because for some plotting, but not for a very special reason. So this is the idea. This will be a very synthetic problem, no images, nothing. It will be just points on space. So what I will be doing here was start with a collection of random numbers, just to show a little bit what we already discussed about NumPy, all those numbers. So how we generate a certain list of values, slices. So this is like catching up on what we did before. So what I will be doing here, and you see my points are on a random distribution that follows a normal distribution of random points. So what I will be doing next, okay, right now I have two different random distributions, normal random distributions of points that are centered on two different locations with different sequence, and I attach those two values. So probably would like to, let me see if I can also plot those. And I concatenate those. So we have 2,000 points here. right there. This is my idea. I have 2,000 points, you see there. And the idea is to make a separation of them using what it will be the precursor of a neural network. A very simple thing. So if you want to see those with colors, I probably plot them. Yes. So this is the idea. Those plots, you can see those blobs of data there. You can identify them. There is still some points that are overlapping. So we will never get 100% separation. So that's something that comes from real life a little bit. And now we'll introduce the percent. In machine learning, in deep learning, in this kind of problems, we always separate a portion of the data for training, a portion of the data for testing. So that's exactly what I'm doing here. That's what I have a 0.8 here, separating 80% of the data for training. And also I think I scramble the data, I shuffle the data here. So because I have all the first 1,000 points are the blue ones, the second 1,000 points are the red ones. What I would like is to have something that allow me to train those. So I will be first shuffling down those and using the same ordering to also shuffle the labels that we will use for them. So the red and blue, correct. So now we have 1,600 training data, 400 for our testing. And you can see how they look. Now I'm plotting slightly different. So now I'm plotting all the points with orange that belong to the test training data. And I am plotting the 400 points from the testing data with a different color. Now you see that all those points are well distributed among the two sets that I want. So this is the idea with a percent. So in this case, we have two inputs, which are the X and Y. So we're calling here X1, X2. Those are the two values, the two positions of the points that we have. This is our perceptron, which has some weights. In this case, it's just 2 weights here and 1 bias. And with that, we will get in a function. The function is a bias plus the sum of the product of the first weight here with the first input here, the second weight here with the second input. You see that it's exactly the same we did for the neural networks. Now, what I have here, let's see, was doing exactly that. So here I have this function. I will start using zero bias, and I just made it. The first weight will be 1, the second weight will be 0, and I am returning the computation of that. So this is my perceptron for any value, vector value that I insert in the argument. So X will be is or NumPy array. And now what I'm doing is applying this function with this thing we saw yesterday in the afternoon about functional programming with NumPy, where we are applying a function to all the elements for a specific axis, in this case, the axis number 1. So it will be all the rows of this for this array, for the array that contains all the. So if you want to see here Z shape is 2000 values, 2000 values in the first axis, 2 values in the second axis. So I am going into insert or change or produce all the values in the second axis. So all those, and the function will be applied 2000 times for all of them here. And I will get in this projection here. So those are the answers for these weights that I was using here for all the points that I have on my training set. You see what I got? That if you look at that projection, this is what you get. You get some points here, there. So there are some overlappings there. So if you are using these weights, this weight is basically forget about the X direction, just keep the, forget about the Y direction. So just keep the X direction. What happens with my projection? My projection will just make those points that you see here on the bottom. And my classifier will have a lot of overlapping here. So a lot of points will be crossing both sections. So this, for sure, this weight and this bias is far from the idea. So the idea is to find which is the right way and the right weights. We have 2 weights here, and the bias that will give us the right result. Now, what happens if we do this, the other option? So I was doing something similar to that, and now this time projecting on the other axis. So forget about the X-axis. Just let's see if I can classify those. Just looking at the Y-axis, the second. Again, we are getting something like that. We know that will be bad. So the idea should be something that actually combines the knowledge from the X position and the Y position, so we can get it right. And so that is the equation that we are using. And what we are doing here is basically a dot product. And so I'm discussing here briefly for those for the undergrad who are not familiar with dot products, what they are, what is the meaning of that. And we are basically doing a projection of vectors scaled by the magnitude of them. So that is what is behind that. So now I am trying something else, before I move into the algorithm, the perceptron algorithm, which is something really, really simple to understand. I am just trying another zero bias, so it's still moving around with no displacement of those points. But the Y, W1, it will be -1, W2 will be 1. So I will be using both. So you can see there that I have like another projection of points. So this will be something like projecting on a vector on this direction, -1, 1. So that is what the code is doing. With no translation, that is what it's doing. So this is the function. You enter an X, which is a vector. I forgot to put the vector sign here. It is a vector. X1, X2 just made that computation. So what is behind that is the idea that we are actually doing a rotation. So under some circumstance, under some angle, there is one angle, very privileged angle, where we can project all those points over the perpendicular direction to that. And we will get the best classification that we can do for those points under those circumstances. So just when the X and Y position, that's what the best that we can do. So here I have the training data. So yeah, just to confirm that we have this. So how this works? We will be creating what will be our loss function. We are saying if this product here, the product of the weights with the axis, the input plus the bias is bigger than 0, we will return 1. If it's not, we will return 0. That is something that will help us to classify the points. So we will tell, okay, this is red, goes into this direction, this is blue, goes into that direction. So we will put a number for those two labels, for those two categories. So the perceptron algorithm works like this. It's very, very simple. You set the B's and W's to 0 for simplicity. And I will be renaming B as a weight. So I will convert in weight in a special weight, which input is always 1. So if you want, we can recast this problem here, this function here, or the function that we saw up there. We can convert this B into a Y and into a W if we assume, okay, no matter what, the first input is always a 1. And there is just a chain of naming that will facilitate some things below. This is what we need to do as many times as you want. So inserting all the points for all the pairs of points, take each point, compute the value of the function, compare the values of that function with the values that we want. So we want, let's say, 1 for reds, 0 for blues. So now we know for each point which is the right answer. So we have a label for them. That's the thing that we are doing here. We compare the answers, and if the value matches, we'll move to the next one. Otherwise, we change the weights using this prescription. So the perceptron is this. The whole point of the algorithm is doing this. If we are wrong, if we predict the point should be red, but in fact it was blue, we will be introducing a small change to the weights. The weight will be the real value, the output of the function, and the corresponding x there. And this is what I will be doing here. So here, what I did was I took the values here for my W. Now I have 3 W's. Remember, I promote the B, the bias, as a weight. Here, I am taking the input and then adding on the first element, I am concatenating just one, the value 1, a constant 1. So now we have 3 values. So now my input became having 3 dimensions, 3 values. The first one is always 1. And now this one is the actual pair, X and Y, or the X1, X2, the actual position of the point. And I am computing the dot product of those. So the dot product of this input times the weights. I am getting 0. I am checking what should be. This is the value of the function. This is what each will get me under my condition. If it's 1, go to this, go to the other option. And that was a 0. So the real value is 1. So I got it wrong. So I will need to change the weight for that point. So I will be using that difference with the weight, and I will introduce that weight here. And I will be moving to the next one. And this one will be right. So I move on. I take the next element. So the next training data and element. And I will be getting another value here. So I got it wrong. So I'm changing again this one. So this is what I'm doing over and over. And this is the whole algorithm put into place and announcing at the end what was the accuracy that I was getting after that iteration of entering all those points and changing the weights when it got it wrong or right. So when you got it right, you change. When you got it wrong, you will be adjusting the weights in the right direction. So you see at the very beginning, at the end of the first pass of the points, I got 95% accuracy. I re-inject those points, I will be getting a different value. So you will see when I'm getting those values, and those values start to moving up and down. And they also vary if I execute this all over again. You will see that. So that's what I get. Those are the weights. So this phi and those two values here will be the bias and the corresponding W's, W1, W2 that we have for the weights. If we have that, we get this value for our training set. So we separate the training set that was not used for building this, and we got an accuracy of 89%. Oh, the first set of weights, we decided, it could be random, but we decided that there will be 0. So we can start from 0. It's right here. The first line here in the algorithm is set B and W's to 0. So that will be our starting point. 0 bias, 0 W's. So that will be for sure wrong, because if with W's equal to 0, so you will be taking nothing. So you will be not using at all the X and Y position. So that is our standard. You will get it wrong, but that will kick the movement of W's, the weights, from the very beginning. What I did here, so 89%. So 89% at the end. This probably did it. I probably forgot to reset some random number generator, and you can get different values here. 99 I was getting at some point. And what I'm doing here. Yes. So now the point is, what is the understanding of those points? What we did, we select those W's will be the direction of the slopes that we have here. And some points will be misclassified, and are those green points, because those were generated from one set, but they are overlapping. So a system like this will not be able to perfectly classify them, because we don't have just 2 dimensions, and we are not able to do much with them. So that is the first idea. So the crucial point here is pay attention to this, because this idea here is what you will be doing if things were so simple that we don't have any hidden layers or something that will complicate that with gradients. So for going into the neural networks, we have to keep a little bit of these ideas. This is the source of inspiration for neural networks, the use of this linear function, the use of a fine operation, so a translation, a rotation, a skewing, translation, a fine operation, and here we are not using any non-linearity. So this is the old, let's say, really the precursor of that. So this one, but you see that this theme continues to be there when we move into deep learning. So now I will be jumping into this one, I think, the mathematical concept behind neural networks. This is just especially for undergrads. It will be some evidence. Sorry for those who are probably more familiar with those. things. But I would like to stress that all that we are doing is really, really simple math. So I will fill in the gaps if for some of you that you feel lost on this, on the idea of vector operations and gradients and all that. So did I close it or not? Okay, now. So this is what I would like to execute. Again, for this notebook, yes, I just put this because sometimes it will not, on the cluster we don't have LaTeX, so I will have to skip a couple of things. And from the notebook, that will not affect our understanding of this. So now we will keep this in neural networks. We keep this idea. We want to go for simple things, simple operations. So this operation here, that will translate in a minute into matrix operation. We will see that in a minute. But right at this point is just a vector inputs, a vector of weights. You multiply those, you compute the dot product, and you get add a bias. Actually, the bias has no. Sorry, the bias has no subscript. That was my mistake. So that's what I'm getting here. So I have an array, and I'm computing this. So what you are doing is basically a rotation and eventually a shift. If you consider that just for one vector, all that you are doing is adding a slope and doing a small translation. Now, those is for definition of functions. Okay, so this is one function, and you will see a few other things where we have functions. Functions could be continuous, but they don't have to be. And in fact, here we have a definition of a function that is not continuous, but it's still a function. So there are no two values for every single point in the domain. And so the codomain, there is just one map from the set of the input to the output, just one there. The same output could have several inputs that go there, but not the other way. So one of the things that we mentioned in a minute is the fact that we are using nonlinear functions at the end of those operations that we did with the neural networks. Those are called activation functions. That is the ingredient that introduces some twisting to the final values. There are two main exponents of activation functions used in deep learning. One is the sigmoid function. It was like the old way of originally back in the 90s, everyone was using the sigmoid function. First, because you have a clean derivative, the derivative probably get it there. It's very simple. An exponent and another exponent in the denominator is really, really simple to get. And also they have derivatives at infinitum. So it's soft, and the derivative is also soft and continuous. So that is a good thing. So back in the 90s, that was the dominant activation function that was used. When people move into convolutional neural networks, large amounts of computation, and everything becomes more numerical, people start using this rectified linear activation function, also called a RELUX. RELUX, that's the name of that. So they are better for preventing some things that happen when you move into deep nets. And one of them is that when you use sigmoids and you put too many layers, the sigmoids will be basically flatten your gradients, flatten the slopes. So it will be harder and harder to correct in the right direction, so that the networks will take longer and longer to converge to the right values. And that's one of the problems with sigmoids. But at that time in the 90s, nobody did a very deep learning because everyone was doing that by hand. By that I mean, you compute the derivatives and you compute what you have to do, all those operations, the chain rule by hand, so that the networks could not be very deep. With the Redux, that doesn't happen. So that's why people have chosen those. They propagate better, they converge better, they are better for, especially for convolutional problems. So you will see all those Redux are always used in convolutions. And here you have, I just plot, just to give you an idea how this looks like, the sigmoid, how they are written. And this one is just returning 0. If the value is negative, returning exactly the same value if it's positive. Okay, just defining those functions. Okay, and you see here some others functions that you can imagine. So you can think about the step function, which is not, you have this jump here, the two different, the sigmoid, also the tangent h, the parabolic tangent, and compare that with the rep. So those are functions, and notice that you can have something clean for the derivatives, or making the same colors for the derivatives. Those things are important because the derivatives is what help us to know in which direction our network should go. So probably just here more plotting in a different way. So showing that those sigmoids give you like a small transition from one place to another. So from one region where it becomes 0, another region where it becomes 1. So that gives us some nice mathematical features, but less practical capabilities. That is the compromise that is not there. And part of the reason, as I told you, is that at some point these curves has very relatively small slopes. So when you propagate, those become lower and lower and lower. So you lost. There is a shallowing of gradients at the end. So that's the message there. So now we will see a little bit what the process of inference when you have a neural network. So that I will go back and into a very simple neural network to regain again what we did for dense networks back again. So here I'm drawing a network, and I put in, let's say, I put some values here for identifying the inputs. I will be having here and hidden layer and the output. So very simple neural network. And here I will put some values for the input, as we did in one of the previous notebooks. And in this case, we have those. Again, I'm making this mistake of putting I, which should not be, with the hidden layer. So we will be doing this operation, and here I am doing what I told you before. We are converting these biases into one extra weight, just because mathematically it's simpler to manage. So just attach that as another weight, the same level of the weights, with the particularities that the input is always 1. So I'm computing that, and you get this value at the end. To this point, I have not executed. See what I did. Yes, so I put the 1 in front of it, and now I'm computing the input of that one by one. So first neuron with the input is receiving the 3 values on the input, is computing that, and is receiving that. But still not using the nonlinearity here, but I will be using 3 equations, 3 operations here to computing that. So you can do it from a different perspective. If you take those H1, H2, H3, and you stack them. So at that moment, you can see the bias is the first element here, and I stack them as columns. So the weights for the first is because I'm multiplying this from the left side. In other books, you will find this the reverse. So you will find as rows. It's just a notation. In my case, I'm putting I am introducing the vector from the left. So here I have the weights, the biases, sorry, and this column here, this first column here, down this 0, are the weights for the first neuron in this hidden layer. And this one is the bias for the second layer, for the second neuron in the hidden layer, and the weights are down there in the column. So with that notation, I will be able to do this with just one operation, and that operation is a matrix multiplication, matrix multiply, and it's central, and that's the reason why it was so good for GPUs to do this, because matrix multiplication is something that for GPUs they are really good at doing this kind of things. And so for those who are not familiar with vector multiplication, especially undergrad, I will just show you a very easy way to understand how this works. So you have 2 matrices here, A and B, and to compute the matrix multiplication, you can imagine this, so you can put this B on top, the A on the left side, and the matrix that we will be computing is right here on this corner, the C. So right here. And what we'll be doing is assuming that we have like here, like a train of values here, and we will be moving those here from A, they will be moving toward the left. Those here on B will moving down. When they encounter the corresponding value, we will multiply those and we will put it in the background. When we find the value for the orange, they will go converge, multiply, and we will add them to a value behind and doing that. So at the end, we will have the beautiful rainbow here for the value that is right there. That will be the computation of the product for that corner, for that specific location of C, how you compute that. If you want to see it from equation, this is the equation. It's not so hard. The point is that you notice that the length of this side of the matrix must be consistent, must be the same as the length of this with the row size of the A matrix. So the column size of B must be equal to the row size of A. That is the condition, because we need to match those correctly. And if you want to see this from the mathematical perspective, the Cij is right here. This is what we are doing mathematically. This kind of operations are being parallelized for a long time, in the 70s, probably even before. So we can take advantage of multiple cores, and in the case of GPUs, all those cores, the GPU core, to make the matrix multiplication really efficient. So that is the reason why. That is one of the reasons why we use so often GPUs on this line, because this is a lot of dense linear algebra, very simple operations. It's just that we are doing those massively. And so here I'm doing this, the dot product here. So this is how you do dot products with NumPy arrays. So I'm taking the input, multiplying by the H. The H will be a matrix, and I will be getting the output of that. So and this is what I'm getting at the end. What is missing here is after getting this operation, the linear function, that's why LF is from linear function. And what I would like is to put them an envelope on that with a non-linear function, and that's what I'm doing here. So I am putting that on a sigmoid, so every single value will be the argument for the sigmoid, and I will be getting this, something that again we can parallelize very easily. Yes, so that is so. And now at this point, what I'm doing is taking the weights here for the output, the final layer that we have, computing all that is same. Now this time, the output that we got before will become the inputs for this final layer. So I am doing now, you see that the number of operation is because I'm putting a lot of middle things in the middle, but they are just matrix multiplications happening there, and at the end a sigmoid. So you can express at the end a neural network just one simple operation if you want to. So you will see here single array. See what I'm doing here. Yeah. So this is what I'm doing here. Now this time I'm just plotting the actual network with the values here, the values that I'm getting here, the values that I'm getting at this level, and the values that I'm getting at this level. Okay. Now to get another visual understanding of what those weights and bias are doing, again, especially for undergrad. This is what we are doing. Basically, we have, I'm making here a set of points here that you will see in a minute. So I am collecting those as pairs. So I have 65,000, 60 more than 6,000 values here. Those are all points in this square here. Those are points here in this square. I plot them. So it looks like a fill square, but believe me, it's just because my points are, I put them with some size, so they are actually covering the whole area. And now we'll see what happens when we apply matrix operations of that. So what I'm doing here is, and you can probably you will skip this. So what I'm doing is I will selecting some random matrices 2 times 2 and see what happens. See what is the effect of matrix multiplications over this tiny or this small blue square. So you notice that some of those operations will be shrinking the output. So the output will be also a rectangle or a parallelogram, but it will be a square, reducing the length on some directions. That's one of the things that is happening here. If you have LaTeX, or when you run the notebook, you will see the matrix that here on one column matrix that was selected there. Another thing that those things are doing are rotations. So you see, for example, here is a transformation that is basically a rotation with some sizing. This one is probably the same. The scaling is not much. It's just pure rotation. So at the end, the message is that when you apply a matrix operation, matrix multiplication of some of points in this and in the clean space, what you are doing is basically rotations, scaling, squinting, so taking a stretch in that, but what is aligned continues to be aligned in this. So all those are different rotations, and if you run this again, you will be probably getting an entirely different set of matrices, but all of them, there are a few things that are preserved here. the idea of straight lines continue to be straight lines. It will be different, so that if our neural networks were just linear operations, all that you will be doing are just one large linear operation, no more than that. And the way you see this is because we only did it here, I think. Okay, and then those are just the matrix multiplications. The matrix multiplications will rotate, will stretch on one direction. That's what those matrix multiplications are doing. Now, another thing, another ingredient are the biases, and the biases are just translating that. So that is what I'm doing here. So I'm taking the square, I'm just translating, just moving into a different direction. So the combination of those two things, translations plus matrix multiplications, are called affine mappiness. So that's if you think I think yes. So here I'm making up before this. Okay, yeah. So the final ingredient. So we have the weights, and we know what the weights are doing. The weights are rotating those things, rotating and scaling and squeezing. And the translations we saw with the square will be moved to a different location. And the sigmoid, for the sigmoid, to visualize that better, I did the following. I have all those points again, and I color them. So I put the color to them based on the distance to the center. So I have a nice rainbow here. And this is the effect of applying the sigmoid to those points. So they will notice that they will move, the size of this square is different. It's going from 0.1 to 0.9, while this one was going from -2 to 2. So that's the first thing. So that is just keeping, it's just scaling everything, but it's also doing something. Notice that this is like a stretch in the corners, in the diagonals. It's like taking that like a flexible thing and you are stretching. So this is a non-linear operation. And that is the special ingredient, or what allowed these neural networks to do transformations that are non-linear, that offer the richness and complexity that otherwise very simple operations are doing, because the math here is really, really simple. So here I'm making the case that if you are just taking one affine operation and we are applying another affine operation to the output of that, that will be equivalent to making one affine operation with another, where the matrix A3 will be this, the product, and the biases will be this operation here, which has nothing to do with the input. So this is a pure translation, another translation, and another affine transformation. So if you just stack networks without adding the non-linearity, you are basically doing just one big affine transformation. So not much of that. So that is to making the case why we put non-linearity in those neural networks. The math that is a little bit behind those things. And this one will be really brief, and I will suggest, I will give you some reference for more things. Here, what I would like to be clear is the fact that we are defining a loss function. The role of this loss function is first having something that gives us how bad or good we are in this function. So we are, imagine that we have the set of all the functions for all the values possible, all the possible values of W. There is one, or there is a set of those W's that will produce the result that we want. So from a big set, we are getting we just want a very small amount of those values will actually give us the right answer. So we need a function that tell us how good or bad we are doing. And also something that will eventually guide us on which is the direction that we should take to change those values. So the next time we are doing better. So you can think something really simple. We did one example. If you consider those just the subtraction, it will be a bad idea. You have some positive and negative values that will be canceling each other. So that using that is not very smart. The next thing that we can think about, okay, maybe we can take the absolute value of those, that it will be better. We can put this using the idea that we have of Euclidean distance. So this is what I'm doing in n dimensions. It will be something like this. And there are other loss functions, and we saw that for classification that we use the cross entropy, which is something that add logarithms because we are trying to undo some operations that we did with the softmax. So softmax and cross entropy loss functions are sort of related somehow. And now the optimization methods. This will become complicated. Let's say, so I will not enter in that. I will just enter in the surface of what is happening there. So the idea is to use the slope. In mathematics, the slope is called derivative. And when you are in multiple dimensions, the slope is called the gradient. So I mentioned here where the word gradient comes from. That is from the Latin, say the steps. So also the idea of walking in a direction, so walking the steps. And here I'm showing a little bit for those who are super not familiar with the idea of derivatives, so what actually we are doing, and also the idea of trying to find an optimal solution. So here we have a very simple solution. So we know here this is a function that is a polynomial. So at least for that, if we want, we can have a formula for that thing. At least in this case, it's simple, and not beyond that. Don't ask me for the fifth. But for this one we can manage if you want. What is the idea? We would like to find what is the minimum of this function. But this red dot is short-sighted, so you don't know the entire landscape. Or another analogy that you see on the lecture is just think about having some fog around. So all that you know is information local to this point, and that information that he can take is how is the slope there, how the inclination of the surface there. So that is the concept of derivative. So what we are doing is moving in tiny little steps because we don't want to jump too far. If we jump too far, we will be probably going into the other side of the world where we have a huge step here, and it will going back and forth. And there are cases where this could go forever. For a tangent, this method of jumping using the slope will result in something like that. But not here. So we are using a small change using the derivative. This is small change between here is something that will guide us in the direction of the slope closer to the mean. This is the very initial point of optimization algorithms that take advantage of the derivative. Otherwise, we have here for this one, the derivative is simple just to plot the derivative here. So you saw at some point here, the slope is 0. So the slope is 0. So you see that in the derivative that it becomes 0. So you will be following the derivative at this moment, and this will move us into the direction where this is 0. This is the idea. When you have more dimensions, well, you have more possibilities. You convert that derivative, and probably that's what I'm discussing after that. Yeah, that those derivatives become gradients. And for computing that, what we are doing is fixing everything and changing just the variable that we want. So here, in this case, I'm putting exactly what we have here, the W's and X, and we are computing. And after that, we have the envelope, that is the logistic function. So we are putting the G, the logistic function, surrounding or taking the input as the output of the function here, the linear function here. So we can take the derivatives of this respect to the W's. But G doesn't depend on W's, they depend on the input. So for that, there is one thing in calculus for those who, I don't know if they already go into that for undergrads, that will take this function here, that is a composite function, and with the chain rule, you convert this function. Imagine that f is a function, you put it here, and you can take the derivative of that respect to that function, to that argument, and multiply that for another derivative here respect to the other variable. So that is what I'm doing here. So I know which is the derivative of the logistic function. Is this exponent here, exponential here? So from calculus, if you don't want to believe me, you don't have the Abramovich with you. It's right here, done with SymPy. This is one of the packages for symbolic operations in Python. And so SymPy will tell me that the derivative of the derivative of this function is right there. And this is what I'm getting when I compute the partial derivatives related with respect to the 3 W's and the B's. This is what I'm getting. So now I can make the composition of those to compute the gradient. The gradient is with this symbol here, this triangle here. This is a vector. So you see here that we have taken as a function that depends on multiple variables, and we are returning a vector. This vector is telling me on which direction I am getting the highest slope, where I'm growing the highest. Well, I don't want to go in that direction. I want to go in the opposite direction. So that's why what those methods are doing is just follow the negative of the gradient. So that is one way of looking at this. I will not go deeper than this quick description. I am just showing you here what happens when you extend those things much further. So here I have the network. This time I am putting numbers on this network. So I'm building the network here on 3, 4, 4, 4, 2. So that this is the network stacked as layers, using another package for networks, for graphs, basically for manipulating graphs, in particular this one. So numbers here. What I would like to stress is that you can imagine that on top of those lines are the weights that connect the inputs that it receives from the left side that will go into building the right side. So on top of those lines, you put those. So you see that there are many, and you see that to get this value 15, for example, you will be depending on the 3 values here. And those 3 values here depend on what happened with the 4 values here. And all those depends on all the W's, each one of them depend on the 4 W's here, all the 4 W's here. So this is like a cascade of dependencies until you go into the very input here. So what I'm doing here is, okay, I have 17 nodes in this. If I don't want to count it, this library will give me how many edges I have on this. And see, if you want to see the whole description of how this is a cascade of partial derivatives, well, this is the equation. It's a summation on all the paths that connect from one input to the out to the location that you want. Of the product, because we are applying the chain rule over and over for all the paths. So it's a very long, complicated set of operations, a product here and a sum for all those, just to get the partial derivative versus something that is not immediately located in the net. So it's right here, equation 655. And in this book, this is the most mathematical book for deep learning. And there is another thing that I would like to show you here. If you want another more visual way of looking at those backpropagation, I recommend you this blog that describes a lot of things. So this one will describe you in more detail that I will have time here to describe the idea of how you collect all those partial derivatives and why we implement on those packages for neural networks the idea of autogradients. So how we store those, because we are changing those all over and over again. So again, this is the equation. I am just computing here what will be a few paths, for example, that will be connecting one neuron with another. So you need to take in account all the gradients, that the partial derivatives that we are getting in the middle of those to compute the final, and getting an idea which is the links that are stronger that will make most of the impact to change the others. So that is a very intuitive idea. So here what I'm doing is extending this for multiple layers. So you see that this start opening a very long chain of operations. And this is a very simple network. So you see that when you do this massively for deeper and deeper networks, all those connections explode. So that's why we store them and we reuse those values a lot during the backpropagation. I have here some exercises on this notebook where I'm trying to, well, I'm suggesting you to try some networks, small, simple networks. So you follow the idea with a small, slightly different architecture. You take those, you compute the input, lead to the output. That is the exercise here. So what I would like to do now, because I would like to cover at least that and leave chapter 6 for tomorrow, maybe. And yes, probably I will leave chapter 6 for tomorrow. Probably will skip some of those notebooks tomorrow because I will not have time. Let's fill this. We solved this for the PyTorch, and in the 30-40 minutes that we have left, a brief overview of what the other frameworks offer to manage tensors. So I will be doing this here. So I will be opening a notebook with Singularity, GPU Inter, 4, okay, 1 GPU. And this time I will be using MXNet right here. So that will probably, yeah, in 4 minutes we can cover that. So for tomorrow, I will be in the morning for sure covering at least 2 or 3 of those notebooks for the for how the different frameworks works. So more in detail of what we did before with the sequential, but there are other ways of building more complex networks. So closer, we will be closer to the frameworks themselves rather than the math abstraction. And at the end, I would like to make some examples with the convolutional neural networks. If and I can, I will demonstrate the recurrent neural networks. Not sure if I can on that. And so now I have, yes, I have this notebook running. Scratch deep learning notebooks, and I will show you here. This is in a small notebook, I think, for MXNet. So MXNet is the third most used deep learning framework today, after TensorFlow and PyTorch, which are by far the leading in usage. It has an advantage in terms of performance and in terms of having Amazon AWS behind it, supporting this framework, and some universities too. So the project is originally for Apache. They have some advantage I mentioned. They support many languages, including C++. So for production, that is important. And as this is supported on AWS and cloud companies, so they put some effort on supporting multi-node training, distributing, training, all that thing. And the fact that you can port the solutions of that, the complex networks ported into system with limited memory, things like Internet of Things, platforms where you are limited in the capabilities, in the hardware capabilities of those. So those are some of the advantages of that. So there are 2 main components to MXNet. One is NDRA, another is Gluon. Gluon is the actual thing that do the neural networks on top of NDRA. And NDRA is the NumPy equivalent with MXNet. So we will see how this works. Again, we take many of the concepts here that we used before. Shape, we have D types, sizes. So let's start. So we can take a list and create, yes. So we can create from list of lists. We can start creating those tensors or ND arrays in this terminology, ND arrays. So we can inspect the shape. We can do things we did before. So we're changing the checking. Notice that here too we have in the specification, if you inspect one object, if that object lives on the CPU or is or has been allocated on the GPU, on which GPU actually. So that will give us more information about that, about the location of those objects. Same thing as before, those ND arrays can do operations, you can do a sum, and so that you expect. So pretty much all that you expect from NumPy. In this case, the start means element by element multiplication for doing for ND arrays, you use a special function for the dot product, the matrix multiplication. And same thing again here, you can take an ND object, an ND array object, and creating and returning as a NumPy object. You want to, and also with the same properties, moving that from the GPU if needed. So it will be allocated on the CPU. So that's so we are returning that. And shape manipulation. So yeah, so same thing. We can reshape arrays. So the idea is that we can do most of the same thing that we do with NumPy. What I would like also the broadcast. So some operations, for example, in a scalar times a matrix, it will be automatically the scalar will be promoted as it were a matrix of the same size without incurring in the extra allocation. So that is same thing for vectors. So this broadcasting is something that we do often. So this is, it looks like we are allocating all these matrices. In fact, this is just referencing just the same six numbers. But now with 2 digits, so they will be returning the locations from memory consistently. So this is a nice trick when you are working with large arrays of data. Broadcasting, we use it a lot in this context. Making copies, so they mention how you will make copies A, B, that will be the same. When you make a copy, you are creating a separate location of memory to copy those values. So even if the values are the same, the answer B is A will be false. So something that you do with that. And the GPU support, which is actually what I really want to stress, is that with MXNet, you have control on the devices, so you can check this, what is, yeah. So here, in this case, I am interrogating if I have access to at least one GPU, what GPU, it will tell me, okay, you are using your device is the GPU number 0. I just request one GPU for this one. And so here I am creating a function, and let's see if I'm here. And here I am taking an array, an ND array, and I'm saying explicitly that I want this array to live in the GPU. So when I compute this, we'll see. When I did it, right here. So when I did this, I put this array directly on the GPU. And this also operations is happening on the GPU. So this is something that I demonstrate here. So I'm taking ones and I putting this on the CPU. The B's, I am putting those in the GPU. C is on the GPU. I am copy A into C inside the GPU. So there is a movement of data there. I am making a computation. The computation principle will be on the GPU. So I'm not still able to see those numbers, the D. I am bringing that back so I will access them. So the D here, those are the values. E is here, those are the values, and those arrays are on the GPU. Something that is beyond what NumPy arrays can do. And same thing here for the low-level operation for serializing the data is using Pickle. So here I have here with this data the A, which is an ND array, I'm storing there. with a pickle. And here I am creating a V, another NumPy array, ND array, sorry, loading that data. And here I'm able to expose that as a NumPy array. So here I have a couple of arrays in the CPU. What I'm doing here. Okay, yes. This is one way of doing it with Pickle. What I'm doing here is storing those ND arrays in the native format for MXNet, which is this .nd array. And when I load it, I'm loading a dictionary. So I was storing a dictionary of a couple of NumPy arrays, an ND array, sorry, ND arrays. And I am storing that in the native format, and I am recovering that as ND arrays. And the idea what the developer said is that they prefer the native method if you're just working with MXNet entirely. So that is the native format for those arrays instead of using Pickle. Let's see what I'm doing here. And here is just showing that after you load that, you can also use the MXNet implementation of that for R if later you want to use that to do something where you feel more comfortable or fits better for R. So still, you can transfer that between languages too. No problem with that. So that is one example where I have an NumPy array. I save it here and imagine that somebody else is taking that from R and is importing the data. So it will load that correctly. And well, this is a little bit more elaborated here. Is the idea the MXNet uses a like kind of hybrid method of achieving some of those calculations. Let's see if I can. Let me see. Can devote time to this? Well, probably not. Yeah, probably we'll see this in another example where I will be actually training the network using MXNet for tomorrow. The idea is basically here that this was created to think about distributing and parallelizing some of those operations that you are doing with tensors inside MXNet, because this is moving into the scaling of those problems. So here you see ways of doing these calculations when you send that into what is called a backend engine, and you see a significant difference in performance. So we'll probably skip this section here. So I have the final 30 minutes here for this one. And with that, we are ready for tomorrow, which is really attached to the practicalities of that, to working with TensorFlow, PyTorch. And so let me close this. This probably is less important. That's why I put it at the end. And the reason for that is that with TensorFlow, we are lucky that we have Keras. And Keras is like a high-level library. It gives us some functionality that isolate us from going too deep into declaring those TensorFlow tensors explicitly. So now the creation of networks is much easier. But before Keras, if someone wants to use TensorFlow, you need to declare all those tensors by hand. So this one will not work here, I think, because I will have to, well, I will kill this I will keep this. And I will create a new one here. For TensorFlow. Oh, no, sorry. Oh, oh. It's TensorFlow 2. I'm not demonstrating it. There are significant differences between TensorFlow 1 to the point where what you do in one is basically completely different when you move into TensorFlow 2. So forget about TensorFlow 1. And I will be closing those. I don't know if it's this one. So this one will be the final notebook for today. Is this one, TensorFlow. Okay, so we have like 25 minutes. So here I'm running TensorFlow with GPUs, so we will be able to do something. So let's start with this. So in TensorFlow, we can define constants this way. Let me see what it's saying. What? Oh, okay. So I'm running with the GPU 24 gigabytes divide 0 is a quadroptic 6 times. Okay. Okay, so this is okay. So in TensorFlow, you define constants. So those are tensors that you cannot change. And variables. So you will see that in a minute. So there is a clear definition of those two entities. And this, okay, it's a constant, a variable, and now you can do operations on them, which returns more tensors. So those are the building blocks of TensorFlow. You can define constants. They call rank 0 tensors. Vectors will become rank 1 tensors, so like list, like vectors. Matrices, same. You can take a list of lists and build a rank 2 tensor from them, and higher rank tensors, like we saw before with when we had batches or images with 3 channels. So those are rank 4 or rank 5 tensors. And okay, same thing. You can take a tensor, convert that into a NumPy, or take the NumPy and convert those to tensors. So same way. And this is the definition of the data types in TensorFlow. So they are called this way. The name are very, very similar to NumPy. So that's really just fine. And there are a few other tensors that will be devoted at the end. So this goes into a more general thing where the tensors could also be like a sparse matrices, a lot of empty connections, empty values. Operations, multiply, subtraction, matrix multiplication is with this special symbol. I think only TensorFlow uses this thing for matrix multiplication instead of the NumPy dot and MP dot or and dot is this symbol here. what I'm doing here, having a constant. Okay, I am just computing the maximum value of a tensor. And here I'm computing a softmax for a set of values. And my C, where is my C here? Okay, this is the C, so 2 times 2 matrix, and I'm computing the softmax of that. So probably if I compute the sum of all those numbers, I will be getting 1. Yeah, probably yes. So you can take explicitly this, convert it to the tensor, getting the maximum value. So, and some things are very close to NumPy, but this framework is probably the oldest today of the 3. So some of the things are not so standard as they are today. So they have the same thing, the same ideas here: shape, rank, axis or dimension, the size for the number of values. So you have that. For example, like here, I'm collecting all those things. The number of dimensions will be the rank of the tensor. So you get 4. No, number of the ending. It will be the rank of the, so it's confusion because it's not the length of that. It will be the shape we provide that. So there is some confusion terminology between those things. Axis, they preserve the name. The axis is okay with NumPy. What else? The rank. Okay, the rank, it would return another tensor. We say, okay, this is the rank of the tensor, which is from another point of view, you call it ending. That's how this works. And the shape. So in this way, you go and call the method directly over the tensor. You get a tensor, and from there you get the value. So the value will be here. Indexing is pretty much the same as PyTorch. Constant, you can get the first element, second element, final element. So it's up to this point is, yeah, it's okay. There is a small difference. I'm trying to see what it is. Up to here is the same. In the left. Yes, it's okay. Converting to NumPy. Okay, you are converting to NumPy because yeah, because otherwise I would do this. Probably to avoid the extra word between. Yes, all those other things that when you print it, the representation of the object is a little bit cluttered. So, so that probably was the reason for that. A tensor 1, 1. Okay, let's see. Go to something more interesting. So slicing. Okay, how you reshape or you get the shape, you reshape the tensor. This notation is different from NumPy, so another thing that changes. Okay, this is also different on NumPy. So this one is on NumPy, you can reshape and leave one of the axes free to fit as is needed. So if you want, for example, you have something like let's say 27 elements. So you can say 3 in the first axis, 3 in the third and the second axis, and what is left in the third axis. So you don't have to be explicit and putting 3, 3, 3. In the case of TensorFlow tensors, what you have to put at the end is a -1. So it's kind of confusing because it's not the final element. It's just saying fit as needed for a reshaping of a tensor. So you introduce the tensor here, the prime 3 tensor, I probably got it here. And the reshaping is, well, it's just different. So I'm trying to capture all those places where I saw some things different. The D types. Okay, the name is slightly different. You put the DF, that the broadcasting works, same thing. With constants, well, same thing. You expand the operations, making some of those tensors look like they have a different size in order to be compatible when you are doing additions, multiplications. Same thing with vectors under some circumstances, broadcasting helps. And what it's doing here, convert to tensor, well, I also that, and those rack tensor, though that this is something particular. I don't see this in PyTorch. Maybe I'm wrong, but not in the last time that I saw. Those are tensors which they have different different sizes on different dimensions. So it's kind of weird, is because usually those tensors are all filled on all directions, but not here. So here you see that if you try to build a NumPy array, for sure it will not work. I think it will not work for PyTorch, as far as I know. I never tested with MXNet, but here you can create a tensor with this. It's like a matrix with some missing values, if you want. It's strange, but this is one of those things that you can do with TensorFlow that you can, as far as I know, you cannot do that with other frameworks. And string tensors, and probably the last thing that I see here are those. Let me see, jump into sparse tensors. So another thing that I think they don't have on PyTorch are those sparse tensors. And in NumPy, they don't exist here. In SciPy, there is a special library for a sparse matrix, for a sparse arrays, and it's called sparse, by the way. The SciPy sparse, but not here. Those are tensors where where what you know are the locations of those that are non-zero. And so for, let's say, big arrays where most of the matrix is just 0. So here I am using just one example from the docs, creating a tensor that have just the values. And this is kind of similar to the way that SciPy works. So you have some indices of the locations where it's not 0, the values of those, and of course the shape. So with those values, the matrix is filled. If you ask for another value, you get just so the SciPy sparse library works a little bit later. So that is what I have for today. I hope for tomorrow we will be far more practical, less of the theoretical side, so more on how we build those networks, the workflows for them, the checkpointing operations, the savings with TensorFlow, with PyTorch, I hope when they make NextNet, maybe I skip MXNet, I'm not sure, it depends on the time. And for the afternoon, I expect to cover one example of the convolution with more convolutional neural networks with more detail. And if I can, in the short time, one of the recurrent neural networks, which is kind of a more advanced thing. This is used for time series. So sound, chirps, or yeah, detecting things that run on the time. So the solutions for that are very different to the convolutional neural networks. And those examples, they are very heavy. So they really need GPUs. And even with GPUs, they take a lot of time. So we will see. We will see if I have time or not to present them. But yes, for tomorrow, it will be chapter 6, 7, and if we can, 8. Thank you very much. And so I think I arranged time for these questions. Please, I have 5-10 minutes to entertain some questions. Otherwise, for tomorrow, those topics, very, very practical. We will just directly with those in practice with those words. One thing that eventually will show tomorrow, because someone asked me for that, is how you take those networks and run those non-interactively. So run those from the command line. So I will make a very short introduction to writing a submission script, running those from the command line, submitting the job from the command line, waiting for the network to be trained, eventually doing some checkpointing in the middle, just in case that something happens. So I will be preparing something like that for more real research practice. And so yes, please, Kyle just send you a message there on the chat. So please fill the survey. It's important. This is the first time that I'm doing this workshop on deep learning. So I am balancing, I am learning how much material I can cover. So this is for me way of experimenting what I can do, what I can do better, what I should remove. So you see that I'm adding things, skipping others. So please fill those surveys because I know that we have a variety of users with different levels of expertise in Python or not, in machine learning or not, deep learning or not. So I need to know the next time if I should put more emphasis on some things or should reduce the emphasis on some others. That will help me a lot. Yes, for sure. I will devote at least a few minutes to 20, 30 minutes to show you one example. I will be preparing something that includes checkpointing, for example. So during the training, I expect to save the best model at that moment, especially when you want to train for more than a week. For big models, so you have thousands of samples. So 1 week is not enough. One GPU will not take care of that. So how you do checkpointing, how you compute that, how you submit the script. For real practitioners, that this is important. So I will devote some time tomorrow in the morning for that. Okay. See you tomorrow. Oh, that's it.